good evening last night, and we have two plenary talks this morning. We have some insights for the speaker.
CV. Brief CV. Please.
Okay. So the first speaker is Dr. Gülserem, and he will speak about 2D materials and especially focus on magnetic properties. He is currently with the Department of Physics with Bilkent University, and his research focus is in condensed matter physics, and he is especially looking into the properties of materials, and today we are looking forward into his research insights, especially about the 2D materials. So the stage is yours.
Good morning, everybody. It's really early in the morning. It's too early for Turkey, especially for boardroom. I appreciate everybody coming in. Today I'll talk a little bit different compared to the superconductivity talks. I'll switch the subject to 2D materials. Then I'll try to give my 2 cents about why describing the magnetic properties of the two materials is difficult, and why we have to be careful to describe these things. So I'm coming from Ankara, Bilkent University, and I'll start with a few slides of introduction. Probably I will not need that detail. I'll go very fast through this. So everything of 2D physics starts with the, I can say, with graphene. That's not that wrong. So at the end of the 2004, when Gaiman Novoselov exfoliated graphene, a single sheet of the graphite, so a new era has been started. So it's a very simple material. So the basic property of these materials is just a single layer of things. In a minute, I'll show actually these are quasi 2D. There might be a small thickness as well, but they show excellent material properties. Graphene itself, very light, very strong, and so on. So these are the well-known things. This actually starts with a very simple property. It has a very simple band structure. When you look at the Fermi level of these pi bands, around the Fermi level, it shows a linear dispersion. Just because of that, you end up massless fermions here, which has the very high mobility because of this special dispersion relation here. Then a lot of properties observed and predicted. One of the recent ones just opened a new era within this field. You just start with a bilayer of the graphene, so this just 2 sheets of the carbon. Then you just rotate a little bit, like 1 degree, very small. So there is no other alteration on the system, no doping, no so on. Then you end up with this magic angle of this Moore pattern, but interestingly, it shows the superconductivity at the very low temperature, but it's a very pure system. It's a quite exotic superconductivity observed this 4 years ago on this system. All these studies, 2D studies, started by Gaiman and Novoselov, so they end up with the Nobel Prize, 2010 Nobel Prize. But today, actually, I will not talk about the graphene. I'll talk with some other materials. So that's the starting point of the iceberg. First, starting from the group 4 elements, the silicon, germanium, and so on. Then next to carbon, boron, nitride. So these are the first systems were tried as a 2D systems, but later on this extended to the transition metal dechalcogenates, then different actually combination from the periodic table and MaxScenes as well. So today I'll talk mostly on these MaxScenes, but there are a zoo of the different materials. Some of them entirely two-dimensional, some of them like the phosphorine shown here shows some pocket structures at certain height, or in I think this one like transition metal dechalcogenates, it's a 3-layer thickness, but essentially all of them are showing the two-dimensional confinement and two-dimensional different properties arise from that. So just to summarize the interest on this system, just look at the number of publications on this one. Obviously, the graphene was the first introduced one. That's the leading one, but you see just a single keyword, graphene, so that includes all sorts of the application synthesis, calculations, and so on, but already a few 10,000 of the publications just on non-graphene, and other systems are rising fast. So today I'll confine on the MaxScenes. That's the new family, but that becomes very popular on recent years because of several applications like the battery applications, capacitor applications, and so on. Today I'll talk about the magnetic properties. Okay, if you are coming from the theoretical area, we have a powerful tool to predict these new materials and their properties. It's just based on the density functional theory. Effectively, this theory is just mapping the many-body problem to just in terms of the density functional. So this multi-dimensional complicated problem is just mapped to a single electron problem via Consham equations. So then we can computationally solve many different systems. So I'll just go past this part. So when you deal with a new two-dimensional system, first what people try, from the periodic table, actually try to match different elements, try to make the different compounds, and so on. So you've checked the stability of these systems, first from the energy calculations, then you look at the mechanical stability, dynamical stability, and so on. So one easy way is just looking at the phonon dispersions. If you end up all real frequencies, then that means that system dynamically stable. So for example, here on this one, there is a branch with the negative frequencies, so that's the soft mode, so this is an unstable, but on the other hand, if you have a system like magnesium oxide, strontium selenite, and so on, these are all positive frequencies, so those are dynamically stable systems. So today I'll talk about the MaxScenes. This is another family, but I'll come this later. Let's skip this slide for the moment, and let's start talking to the magnetic properties. Okay, so first I'll give a very fast, short review of these systems. So obviously, besides these exotic properties, the magnetic properties also attract a lot of attention. People try to establish magnetic 2D systems as well because of the several applications, the spintronics, nanomagnetisms, looking for new materials, robust magnetic properties for all sorts of the applications. So there are two different type of the approach. We might have an intrinsic magnetism. So on systems like chromium 3 halides, so for example, chromium 3 iodide and so on, I'll show some data on that. These systems are synthesized and they are exhibiting these magnetic properties. But besides on that, there are systems with the extrinsic magnetism. So for example, if you look at the graphene itself, carbon is non-magnetic, but when you introduce the defects, the vacancies and so on, you can introduce magnetism on those systems as well. So actually this brings a lot of flexibility, so you make the engineering of these using defect engineering, functionalization, doping, and so on, but that brings the difficulty as well. So just I can extend that to the challenges. So first of all, the important one is the ambient stability. So these systems should work on under the ambient conditions. Then you can show the prototype. Then scalability is important for the many different device applications and so on. But at this stage, actually, what is more critical is, for example, the transition temperatures. So this has to be at least, for example, operate ambient temperatures. So usually the calculations and experiments done at the low temperature, cryogenics temperatures and so on. So understanding or establishing the material with the higher transition temperature is also important, one of the challenges on this system. So there are obviously two different type of the approaches. People experimentally try to establish this type of the systems, but besides, actually there are several theoretical approaches as well. Once you predict a system with high magnetic moments and magnetic properties, then you can convince the people go and try to synthesize these systems and so on. So here I'll provide a long list from this review. Many different systems tried as a ferromagnetic, antiferromagnetic, different systems as well. As I said, because of these promising applications, the effort is huge. People try to establish these things. Here, okay, what I'm just showing in recent years, especially, is several studies just appearing on the literature, and now even we have some reviews appearing around that. But let me start. What is the challenge here? From theoretical side, I'll confine over the theoretical science, but from experimental side, as I try to say, to establish stability at the ambient condition. Even, I mean, you can introduce the defect, but the controlling the defects, engineering, and so on, these are the challenging things. But from a theoretical point of view, actually, I can try to, prepare a slide, then I remove that slide. On the single material system, let's say, from the magazines, let's say titanium carbide, I can show at least 10 or 15 papers, calculations, all published on established journals and so on, all reporting different numbers. regarding the transition temperatures and so on. So for example, you need to use one way of analyzing this is just introduce the Heisenberg Hamiltonian, then you have to parameterize the J parameters, the coupling parameters in the Heisenberg Hamiltonian. In order to that, you start from the density functional theory calculations. For different states, just using the total energies coming from the DFT, you can solve for these coupling parameters. Then using the Heisenberg Hamiltonian, you can go and do the Monte Carlo calculations to get the Curie temperatures and so on. But that part of the literature, I believe it is very dirty. There are some important gradients might be missing. So today I'll try to address one of them, simply the Hubbard model and the DFT plus U. What I'll claim, actually, you will need this approach to have correct numbers for the coupling parameters and get the correct description as the transition and so on. So, I mean, the answer is actually simple. Why we need the Hubbard correction? Actually, on these systems, mostly they include the transition metals and so on. So there are d electrons and even system with f electrons. So these are strongly localized electrons. So if you start from the standard DFT, the self-interaction is not described properly with the ground state DFT calculations. So especially for these localized orbitals, we need some correction in order to proper description of this sky. So if you start, I will show a couple of examples. You will clearly see within this standard approach, standard ground state DFT, I mean, the well-known deficiencies, for example, incorrect estimation of the band gap. Usually you predict the lower band gap with the LDA calculation. Even sometimes you end up with the metallic state instead of a small gap and so on. So obviously, once you have some deficiency in the electronic band structure, then that will reflect to the structural properties than the magnetic properties as well. So this is, I think the reference will come in the next slide, sorry, it's missing. So I'm reporting this from literature, nickel oxide and the iron oxide. So these are standard DFT calculations using the GGA functionals. So if you look at both of them, is not correct. So here in the nickel oxide, you see there is a gap in the density of states, or this is the energy levels. There is a gap, but that gap is underestimated, and the oxygen p states here, this green line here, this is the edge of the valence band. It just appears at the edge of the valence band there. Then on the iron oxide, that's more severe. Actually, the Fermi level is set to 0 on both of the plots. The Fermi level is just within the band, and no gap at all. This is predicted as a metallic ground state from the GGA calculation. Obviously, both of them are wrong. I'll show the correction in a minute. You will see the difference. So we need to some fix of this self-interaction, correctly describing the self-interaction of the electrons within the standard DFT approach. So in recent years, several methods developed. So You might go the hybrid functionals. So instead of just using LDA, GGA, now the HSC type of the calculation becomes more common. In these calculations, then you will see the band gap is expanded and it goes to the correct direction, approaching to the experimental values and so on. Then even some more complicated functionals are developed, just using, for example, second derivative of the electron density. You might end up with the meta-GGA and so on. One easy way is the so-called DFT plus U. So you include a Hubbard U parameter as a correction to the DFT Hamiltonian. Then you can place these localized D levels, F levels, whatever it is. Then you can end up with the correct band structure, and you can correct these properties. So there are two approaches, but I'll talk them. If you are not familiar, the term is very simple. So this is the Hubbard Hamiltonian. So we have the standard hopping term, the first term. Then we have this U term. That's the like on-site electron-electron repulsion term. So we have this U is the what I am referring as the Hubbard U in the DFT plus U corrections. Simply, if you look at it as a correction, DFT, actually I'm not. On top of the DFT, we might have this Hubbard U correction. We have a simple term just introduced by Didorov many years ago, a simple form of this correction based on this density. But calculation of that is not that simple. But let me first convince, just revisiting these previous examples I showed. So this is the iron oxide band structure, which is predicted as the metal. So this green line is the Fermi level. You see that's just within the band. With that correction, this band gap expand. You see in the band structure or in the density of states, this is expanded, and you get the correct antiferromagnetic ground state, just including that U term here. So, okay, so this is working. How this can be fixed? So the easy way of doing this is a semi-empirical approach, but within this semi-empirical approach, if you are lucky, then you might end up the optimized value. So here I'm just showing one example. This is based on the anatase titanium dioxide. So the valence band, the d orbitals of the titanium just dominate the first valence band, and that's quite critical. That's in that region. But the band gap from the standard GGA calculation appears like a 2.7 or 2.08 electron volt. That's too low. That's too low compared to experimental value, which is 3.2 electron volt. So with this semi-empirical approach, what you can do, you can introduce the U value, then do the calculation, look at the band structure. So with U is 0, as I said, this is 208. Then for different values of the U, you see the band gap is increasing up to a certain point, then it's decreased again. So if you try to get the experimental value here, 3.2, so you need to use a U value like a 7, something like this. But the problem here, you have to look at the structure as well. So while you are correcting the band gap, you might distorting the structure, geometrical structure, and so on. So this is it's really empirical. You are just trying to fit some data and try to keep all the properties intact. So not always this is working, and obviously if you are doing the first principle calculation, this is not the quite correct approach. So in recent years, ab initio, first principle determination of the Hubbard parameters introduced and studied a lot. So starting from Hartree-Fock-based methods, several of them introduced. I'll just show the linear response approach and the recent implementation based on the density functional perturbation theory. So very quickly, in the linear response calculation, you can just follow like this. So if you do as with the different number of the electrons, if you do the DFT calculations, that solid curve compared to the exact ones, so this is the discrete points, actually there is this difference. That difference has to be introduced as a correction. That difference is just shown as the blue curve. That was introduced on this paper within this linear response approach. So the basic idea is this, so that's summarized here. So we have this term, this projection term included with the black part is the standard Kohn-Sham Hamiltonian. That part introduced as a, so you, on this approach, you introduce a supercell, then you perturb the atom, then you look at the change in the occupation numbers. This N is the occupation numbers or the density, you can say. Then based on that, you can calculate the chi, and that difference, perturb and perturb, will lead to the Hubbard parameter. So a couple of years ago, actually, this was expanded using the density functional perturbation theory as well. So here you introduce the perturbation within the unit cell like a phonon calculations, but with this DFPT, actually you can do the calculation in the small primitive cell and exactly like the phonon calculation, you can calculate this, and this was implemented on this paper. So here, this is just comparing these two approaches here. So in this one, you need a large cell in the real space, then the Q mesh might be small. With the DFPT, you have a primitive cell, but then you need the converge K points. This table is just summarize that. But with a smaller cell, actually, you get a much faster, well-converged results, and so on. So this is just shown on copper oxide, nickel oxide, lithium cobalt oxide on 3 different systems with the convincing results. So one critical thing is here, you have to be very careful about the convergence of the computational parameters. Here again, from this paper, this is implemented in Quantum Express HP.X code. I'm just reporting this convergence from this paper, very same paper. As you see, with the Q mesh, so these are different K points, so use this for the Brillouin zone sampling. This is for the reciprocal space, like the Q vectors of the phonon calculations. There's a strong change on that one. So this is for 3 different systems. All these 3 different systems shows these fluctuations. Actually, you have to well converge both K and in terms of the Q. So that's the one critical thing of this perturbation theory approach. Then another critical one is to determine this U parameter in a self-consistent manner. Okay, so in the empirical one I showed you, you get compare with the band gap and so on. So within this approach, this is fully ab initio, and you can do this in a self-consistent manner. Then you get the this might be critical. I'll show you will see. So you start with some initial structure. You relax that. Okay, you get the ground state of that. Then you do the for DFPT calculation. You get the value of the Hubbard parameter. Then with the Hubbard parameter, you check the structure again. Then from that structure, you get the Hubbard U. You compare the initial one and the out. If they are same within the tolerance, then you said both the structure and the parameter converge, then you can continue with that. Otherwise, you return back, you relax the system, you do the Hubbard U calculation again, and so on, so on. So this is important. So let me make this comment. In the literature, actually, this type of the calculation appears very recently. In the literature, if you look at this Hubbard U calculation, usually they say a number without this type of the tests and so on, and just using that number for any system. Okay, it says like an iron oxide and say, okay, for iron, I'm using the U parameter as 4 electron volt. So it might appear in one system, in one calculation. So the usual approach within the literature, just using that number without verifying that and so on. But you will see that actually this structural optimization, the self-consistent approach is really important. So we studied that. So this is another example just showing this approach is working. But let me directly jump to our system. So we explored this on the Maxines in detail. The Maxines is became very popular in recent years. That's introduced 2004 by Gogotsi and his workers. The system is very simple. The chemical formula, the max, you start from this chemical formula. M is this yellow part. This is early transition metal here, okay? Then the X is either carbon or nitrogen. Then in between, we have this A, this green part from the periodic table. So on that max phase, that's available as a bulk for many years, 30, 40 years, this is available. So the bulk structure is like that. The thing is, it's a layer structure. So on contrary to the graphene, in the graphene, the layers come together with a van der Waals interaction. Here, they come together via this group A element. So these blue balls are just from this part, for example, aluminum is just connecting these different layers. Okay. So you can start from this bulk material, then very easily you can etch this elements here. It can be one of these. Usually it is aluminum. You can etch the aluminum away, then you end up with these Maxine layers, two-dimensional materials. And in recent years, several applications are just predicted, confirmed on these systems. So here, we start with the pristine form, both the carbon and the nitrogen one. Okay, this is quite boring, but just don't try to read. I will show the graph of this. What I'm showing, so we have some different transition metals from row 3, row 4, row 5, and so on. What I'm showing here, three different states. So this is the non-magnetic one, ferromagnetic one, and antiferromagnetic one, each calculated self-consistently. That's each relaxed geometry, U calculation, and after end of this self-consistent cycle, this table established. So what this tells, the first message from here, so for example, just pick one of the guys. So for example, vanadium carbide, the second row. So the lattice constant, non-magnetic, it is 2.9 angstrom with almost 5 eV U parameter. In the ferromagnetic states, obviously, lattice parameters change, this lattice expand, and the U parameter is also different. Instead of 5 eV, now that appears like a 4.8 eV, and in the antiferromagnetic states, actually this is completely different. It's like a 4.2 eV and much expanded lattice. So with a single U value, obviously does not correctly describe each of these, even within the single material, these changing. So this is my first message. So if you look at the same data for that, so this is the U parameter, so this is the row 3. So there's a trend, slowly increasing trend. Even some peculiarities, for example, mangan shows us peculiarity over there, nickel as well. But for group 4, group 5, more smoother. But there's a variation even within the 3 different phases of the very same material. As I said, so for example, in the nickel, you see the antiferromagnetic U is much, much different than ferromagnetic or the other one. And the lattice parameters obviously is changing as well with the different phases. Then very quickly, so if you look at the, now, this is just reporting the magnetic moment for this system. So you see, for example, titanium carbide, ferromagnetic, antiferromagnetic, but these each calculated with the U's, as I said, from the corresponding phase U. Not the single phase, not a random one, self-consistently calculated U's there. Then here we just report their ground states. You see many different variations, and some of them are non-magnetic and so on. Sorry, this is just a bunch of numbers. The bar graph would be nicer, but in the last maybe 1 minute, let me summarize. So what's happening, the basic physics here, I can just give one example. Similar things happening. So this is the density of states, okay, for the non-magnetic states. With the U parameters is 0, is this pink or the red one. Then the convergence U is 4.05 eV. This applied titanium 3D orbitals. So when you applied, you see from that pink shifted a little bit with the non-magnetic one, but not that much. So if you, sorry, if you look at here, we have like a 1.2 Bohr magneton in the ferromagnetic states, 0.85 in the antiferromagnetic states. Magnetic moment, and its ground state is the antiferromagnetic. Just keeping that in mind, if you look at here, so in the antiferromagnetic state, as you see, the shift is much appreciable. You can see this is U0, then the light blue is with the U applied there. You see that those peaks are shifted down there, and that shift actually different for the up spin and the down spin, and that splitting leads to this magnetic moment. And so essentially, I mean, this is similar. I will not go one by one. You see with the U, parameter. This is for chromium carbide. The shift is, this is up spin, down spin, d orbitals just moving different directions, opening the sometimes gap, sometimes lead to the semi-metallic cases. Placing these localized orbitals on the correct place, you end up with the actually correct description and so on. So these calculations carried by the Sibel, and this is a collaboration by this team. So my main message here, actually, you have to incorporate Hubble-Q correction to describe the magnetic properties correctly, and you have to determine these self-consistently. So just a number picking from the literature is just given some correction, but that's not the correct one, as I clearly show. Even within the same material, there is a magnetic phase, different magnetic phase described by a different Hubble-Q parameter. Thank you very much.
Thank you for this very interesting insights into the 2D materials and the parameter extractions. Do we have some questions? I like to start with a question, and you introduced the approach by using the density function, and my question is about including the temperature in the modeling. So how does the parameter depend on temperature, and is it possible to extract?
Okay. So actually, I just concentrated over this part, and I just didn't show the slide. So in order to study magnetic properties, what need is the initial stage is starting from this density functional theory calculation. Yeah. So with this, so for example, this is one of the systems. What you do, this is tough here. You introduce different spin configurations. So we might have the ferromagnetic one, then in the antiferromagnetic, we might have the different structures. You do the DFT calculations on all of these systems, then using these energies, you can solve the coupling parameters, J1, J prime, and so on for the Heisenberg Hamiltonian. So actually, you need this second calculation. Once you have the Heisenberg Hamiltonian, a couple of different approaches might be possible, but the most common is the Monte Carlo. Then you do the Monte Carlo with those parameters. Then you get the specific heat, the transition temperature, and all those properties. So I didn't show that. I'll just concentrate the initial stage, since in the literature, these J parameters, in different papers, you see the different J parameters and so on, but it should be unique for the same system. With those correct J's, then you do the Monte Carlo or similar calculation for the temperature.
So, is there any other question? I don't see further question, but we have plenty of time after the plenary talks to talk to you. But before we switch to the second speaker, I'd like to thank the speaker again.
Thank you. Thank you.
So we have a second plenary presentation, and we switch to the topic of hybrid Josephson junctions and opportunities for quantum hardware and some advances in this technology. And in this case, the presentation is given from Francesco Tafuri from the University of Napoli from Italy. Okay, yes. So we have a short time for 2 announcements.
So I'm very pleased to inform you that in this excellent program, you are invited to contribute to the proceedings of this meeting. It will be published as a special issue by Condensed Matter, that is an international journal that is very high standard. I am the honor to be chief editor, and we are happy to invite you to contribute to this. It's open source, and all the participants can contribute. The publication organization, I follow the quality of all papers, and we have a very high, very good referee. All the referees are selected to very high standard, and the editorial staff help you for all the editorial templates and everything. I am very proud of this journal. It will be indexed in Thomson Reuters with a very good impact factor. And so I think it's a journal really adapted for this kind of physics, new quantum material, complex matter. So I invite you really to contribute to the...
Two more sentences. Yeah. Finished?
Yeah.
Okay, I think this is being recorded on YouTube also for others who are watching us from the internet. And we agreed with the journal, and Professor Antonio did not disclose it, but they will waive the fees for plenary and half plenary. Yes. Plus, they will make 50% discount to invited speakers. And our conference organization will pay this 50%, so no one will pay if it is accepted.
Yeah.
Okay?
The open source today is very important, so the aim of this journal is to keep a very high quality and open source. So all people are very proud of it. I invite you really to contribute. So practically, it will be a big impact for our community.
Well, thank you. Also, just a small announcement, we will have excursion, and we will hope to be back at 7 o'clock here. I think we will have 2 a la carte restaurants to catch up the 8 o'clock memorial session here. And for those who would like to have fish, sign up, and for those who would like to have Turkish kebab, sign up. 2 separate groups, okay? Thank you, and let's go for the second plenary speaker, dear friend Tafuri. And
yes. Okay, thank you for this very good opportunity for the publication. And with this, we switch immediately to our presentation. So, Mr. Tafuri, the stage is yours.
Can you hear me? Yes. Thanks so much. I would like, first of all, to thank the organizing committee, and especially Ali Genser, for the invitation in this beautiful place, in this beautiful conference. I'm going to talk about the work we've been doing in Napoli on Josephson junctions in a long time, and try to answer also to the question that Ali asked yesterday, why students should pick a topic. And I will try to also, with some kind of general review, extensive review, to understand why the Josephson junction okay. Down. Okay, down. Okay. Why Josephson effect is, the wonders of the Josephson effect. It's a pleasure to acknowledge the group working in Napoli. First of all, Davide Massarotti, Domenico Montemurro, who are, young professors in Napoli. Yesterday, Davide gave the talk on about very detailed aspects. And then I'm going to talk a little bit about the work that Ali Mahmad, Luigi Di Palma, Alessandro Miano did about ferromagnetic junctions and phase detectors. And then also would like to acknowledge Gian Piero Pepe, who shares with me a lot of responsibilities for this research. Then also we have a long-standing collaboration with Theory Group in Napoli. This is our Vulcano de Vesuvio, Napoli, and Arturo Tagliacozzo and Saro Fazio. And then also a lot of the things I'm going to discuss later in my talk are due to an intense collaboration with the SIC group. Actually, SIC is a company in the States, but has a research and development lab in Napoli led by Marco Arzeo. And so the group is led by Oleg Mukhanov in New York. This is a picture of most of the people in the group. I couldn't do like Jacopo yesterday, the collection. It was not so good, but there are different people. There are some overlaps, and there are also some people missing. And also a pleasure to acknowledge some collaboration. There is long-standing collaboration with John Katie and group of Floriano Lombardi and Chalmers, because I'm going to review also some older stuff. And then long-standing collaboration with a group of Mark Blameyer at Cambridge University, and then some recent work with a group of Carmine Granata, Antonio Vettoliera, Siena, still close to Napoli. The starting point is that really we never had so many different types of Josephson junctions. That's the starting point of our discussion. And this is due to novel materials, unanswered interface compatibility, novel types of barriers and nanoshapes. So this gives amazing possibilities to investigate exciting physics. Actually, a Josephson effect, the nano meets the macro, and we'll see what it means. And then here, we really apply quantum mechanics at the macroscopic collected variable. And then, we'll also discuss how we can really measure the macroscopic quantum. That's really important. So the Josephson junction is the tool to measure this phase information, which is in general associated to microscopic entities, is to a circuit. And then, obviously, a Josephson junction is a playing ground where coherence and dissipation fight against each other. Obviously, Josephson junction can be the answer for a lot of questions. For instance, fundamental questions. For instance, we know about the wave. We will briefly get into that shortly. And then one of the main ideas that also we had some talks during this conference, the idea of putting functional barriers and to have hybrid junctions have been the basis for a lot of proposals to see, for instance, Majorana fermions and topological insulators. And yesterday, I will get at the end also the talk from Nicola Poch and Van der Waal, structures with high TC materials. And then another example is ferromagnetic triplets. And yesterday, Jacopo Santamaria gave a very nice talk on this aspect. Obviously, there are a lot of applications you can think about, and we'll revise some. Obviously, the big one is now the big qubit application in quantum circuits. We'll get into that soon. So these are different kind of structures. These are nanowire based. Here we have topological insulators with flays, graphene. Then the new class of two van der Waals materials, and then we have more classical aspects like the ITC and ferromagnet barriers. In any case, Josephson junctions are believed to be the keys to answer to a lot of questions. That's our starting point. Then there is something that we should never forget. These are, about wonders. Their special properties. Actually, the collective quantum nature gives us the opportunity to use quantum sensitivity. That's something that we use and we forget how powerful it is, how it's important that we quantize a circuit. It's something amazing that sometimes we forget. And then, obviously, superconductors, all of us know that there's some kind of special properties that they do ideal elements for quantum memories, amplifiers, detector, high-speed processing, and operating over a wide band of microwave frequencies. All these make these ideal candidates for the miracle we are going to see. So basically, the first point is to show that there is some kind of primary quantum macroscopic effect. That is the fact that we're working on the phase of the superconductor. And this obviously is enriched by our capabilities of nanopatterning and of using different materials. But we have to be aware that basically what is used in the qubits is this capability of secondary quantum macroscopic effect that is the real secret of these junctions. So it's for that we can have this kind of magic and pass from a Josephson junction to these circuits, the quantum computer, with all these amazing, so here's our basic, but then we enter into readout, control, all superconductors enter different levels of this amazing product of our technology. And we should, I like always to start from this sentence from John Martinis, that actually the superconducting qubit research started in the 80s when we were asking, in particular refers to Tony Leggett, where macroscopic variables would behave in a quantum mechanical fashion. And this, I'm going to revise quickly these experiments shortly, has been shown by macroscopic quantum tunneling and the existence of quantized energy levels. That we will get to that, and we'll see how these are very special fingerprints to understand the phase dynamics and so to establish if a junction can be used in a quantum computer. We know these are the basic fundamental Josephson equation, and here's our primary Josephson effect. All you can find in the two Bibles of the book of Antonio Barone and Gianfranco Paterno, and the book from Costa Rica. And here you basically find all possible responses of the phase to the electromagnetic fields and how the circuit approach how to place this junction. And obviously, in general, we have to take care about these two energies. Josephson energy depends on the critical current and charging energy to capacitance. Everything will depend on these two energies. And also, obviously, on how the junction is coupled to the rest of the circuit. This is a typical Fraunhofer pattern that we know has a figure merit of the junction. But this is the first step, and this is what we call the primary quantum effect. In general, we refer to the case where the Josephson energy is much larger than the charging energy, and where the phase is well defined. That's what most of the work has been done. Now, we have been more and more aware with the qubit advent that it's very interesting also the other regime where phase and charge are not anymore, they play together. And to understand that, and I will get in some detail later, this is the washboard potential that describes the potential of the junction as function of the phase. Through the macroscopic quantum tunneling experiments, we have proved that these levels exist, that we can have macroscopic quantum tunneling of the whole phase, and so we are entitled to quantize the circuit. That's the basic idea which is behind the qubit. So if we can do that, we can build Hamiltonians, we can build circuits, and we have fun to build complicated circuits and to start the qubit era. And obviously the two extremes are when we have very well-defined charge and well-defined phase, and this we know associated to charge qubit, phase qubit, and so far. And we also know that the transmon is the most advanced and also most used, because this solves technically some problems, and this intermediate regime of charge and phase, and is the one more used for all quantum computers. So again, these are the three steps. First, be aware of a collective degree of freedom. Second, experimental observation. So we have to prove macroscopic quantum tunneling and quantization of energy levels, and then we are entitled to believe that we quantize the circuit. These are the steps to follow for whatever kind of technology to be able to be used in a quantum computer. Also, we should not forget, especially if we want to do circuits and to put inside to make it work, that there is something special about Josephson junction, which is the only nonlinear and non-dissipative component. So this property is important for the operation of a lot of superconducting circuits. It's important also for the operation of our transmembrane quantum computers. And but it's, this is the first part. Then there is also some other part, which is connected to more classical superconducting electronics, again connected to Johnson junctions, that we can have, some transition through magnetic fluxes, and this is the basis of, the two logics, apart the voltage pulses, which is the latching logic, the RSQ, which is quite spread in the superconducting community, and there are a lot of applications. And this is from Oleg Mukhanov. I would stress here, without getting into details, that this can work to the hundreds of gigahertz. That's the important information. Then, obviously, there is something magic about the rings. Not only mesoscopic physics, but also in superconductivity, and then we have the squids, and we will use that. So we have some kind of loop with two junctions, or one, depending if RF or DC. And just getting to that as utility of every ring in geometry, and so this gives also the opportunity to talk about the pi junction. This is the experiment for the proof of D-wave superconductivity. Here, we have also the pleasure to have Dima, was in the original papers in the 87 when it was proposed for ferromagnetic junction. So you have a ring with a junction. If it's a junction, this is the energy profile as a function of flux. If you have a pi junction, like happening for high TC superconducting, this tricrystal geometry, here we have three junctions, but basically it's important just one, to have an odd number of pi junctions, and this is the definition of pi junction. You can have something very special. This is the energy profile, and here you will have a minimum which corresponds to have half-flux quantum. So you will have some kind of spontaneous current that is the proof of the D-wave superconductivity. So here, before it was some kind of powerful result. Now it's so well established that we use that to prove the physics of pi junctions, the wave, and also to understand the power of the ring. But this is inspiring. If you want to test other superconductors, other ideas, you need to do that, because this, again, is some kind of smoking gun experiments. You get or you don't get. If it's the wave, you need to get the half-flux quantum. If you have unconventional permittivity, you need to have that. And here you can also see all other vortices as opposed to half-flux quantum. Here also break symmetry in this case. This is, again, a very inspiring experiment and with a lot of exciting physics. Again, here it's, I would say, another milestone, in my opinion, group of Zhenya Idishov. Here is an RF squid. It's very common today to talk about unconventional critical current phase dependence, and this is the proof that in bicrystal D-wave junctions of the relevance of the second harmonic. So again here, if you have the tool to try these experiments and to prove that if there are other components, the current phase relation, they are important. These are very, it's something very well known from classical superconductors that, this is, the A is the tunnel-like model. And then if you're in a weak link, there are other harmonics contributing. And in special dimension, you even lose coherence, or the superconducting coherence, for instance, when the micro-BG is too long as opposed to the coherence length. But this case also from very transmissive interfaces, you know that you can have some relevant additional contribution from higher orders, and you will see that in this relation. So it's something that is very established, and again, we have the way to prove that for whatever kind of junction. So there is some kind of clear path to follow if you want to claim things. Okay, so basically, after this general introduction, we'll discuss, we'll take into account these keywords and how the Johnson effect can be useful to build smoking gun experiments and more efficient junctions for quantum bits architecture and sensors. Here, obviously, we should, it was already clear from the slides before, but it's always good to to keep in mind that basically Johnson junction is sensitive to magnetic field, RF field, but depending on the barrier, you can also have some kind of gate dependence on the critical current. This is the concept where there is the gate mode we're going to see shortly, and where there are a lot of applications, the hopes why you put a semiconductor. All the physics now that we are discussing basically use this kind of special material which are sensitive to the gate. Obviously, something that we take care by considering phase dynamics is that we can measure in junctions fluctuations. That's amazing, that by measuring fluctuations, we can reconstruct phase dynamics. So about qubit, we know that superconducting technology is the leading one toward a scalable quantum computer. We know that all computers are based on aluminum technology, except very special case now, a couple of cases. Then we know that Johnson junction, as I told, wonders of nature because they can be quantized and can bring quantum mechanics at the macroscopic level. And we know that transmons are key structures. But we also know that we need to improve scalability, error correction. There are a lot of issues to be solved. And from my point of view, I'm happy that there are also some kind of hardware issues, so that the quality of the junctions needs to be improved. So something else has to be improved from a technological point of view, and something else has to be understood also from a fundamental point of view. This, again, is just to be self-consistent, and here I'm not going to comment all different kinds of qubits, but what I want to comment here is that, there's always some kind of counterbalance. You have advantages, you have disadvantages. Some kind of layout allow to solve some problems, some others they don't. And this is the story which now brings to transmon and fluxonium, why sometimes it's better the other one or the other. Here we have some kind of very nice reviews. It's just very reduced list. And then once you have quantized the circuit, you can build the circuit whatever you want, and this will be some kind of very nice way of building Hamiltonians and build the circuit. We'll see how later we can do that very, very easily. And then this is also the progress of coherence time of qubits that are impressive. In 20 years now, we started from 1 nanosecond to about 1 millisecond. That really can change. So I was talking before about the possibility of gate. I was talking about the possibility that we need to, there are things to be improved. That's why, these are, I said, I picked from the lecture without any real order. They are disordered, and doesn't mean that these experiments are better than the other one or two are not. No, but there are some kind of fancy and first reference experiments about the use of nanowires in junctions and this possibility of tuning the critical current by the gate. And this is somehow the follow-up of work in the 90s. There are some examples from the group of Takagi and Haji where he proved some kind of mesoscopic effects in where you have when the barrier is a semiconductor. And this philosophy is behind the proposal, is behind the proposal of the gate-mon. The gate-mon, is a possibility to use other hardware, but basically is originated from the fact that not everybody is happy in the transmon design to have the flux line, which gives a lot of noise. So, as an example of solution for some kind of hardware problem. These are other examples from the literature, evidence of topological superconductivity, twisted electronics, topological superconductivity, again, without a special order. They are beautiful works with a lot of amazing technology and a lot of beautiful results. And also, these, again, induced superconductivity in quantum spin Hall edge effect, topological insulator, bipolar current, supercurrent in graphene. And to the point that these junctions have been also suggested as possibility to observe Majorana fermions. And we also heard discussions and proposals here at the conference. Again, here, the point is that fundamental periodicity changing. It's here. So we are talking about a different one from those I showed you before. And again, also in this case, we may have a ring, so we have some kind of example to follow. This has been made for ITC, that we should have some kind of different periodicity on the flux. And these are two examples I've introduced you before. Another way for detecting some very, Majorana physics is, being proposed a fractional Josephson effect. Here an example of current phase relationship, similar to the technique shown before by Idishev. And again here, I'm just mentioning two experiments, Andrei Zakin here at the conference and Akira Furosaki. Just the point that the presence of same integer Shapiro steps is not always some kind of sure condition to determine if there are fractional Shapiro steps. And because if you have some kind of non-sinusoidal current phase relation that is typical of highly transparent superconducting barrier, you may have also these additional steps that are not necessarily related to Majorana fermions. And here other examples. And here, for instance, again, from Molenkamp group, obstacles for the observation of fractional Josephson effect. There are other effects to take into account if you really want to trust in all fractional steps. So all these beautiful experiments are great. My point of view is that it would be nice to have some kind of electrodynamic characterization, and dissipation would be beneficial to set some more points and to see the really limit of these techniques and these junctions. What do we mean by phase dynamics? Phase dynamics is the capability I just sketched before of understand what the phase does as a function of time. Here's a very simple approach to the circuit of Josephson junctions. This is what is called RSJ model, and we can build this equation where we have the capacitance and the normal resistance. So what is beautiful is that we have some kind of mapping of the IV curves on this graph of the potential as a function of the phase. And so by changing the current, we have a picture of what the phase is doing. And by doing these measurements, we have an exact representation of the phase in this potential. And this is the base of the macroscopic quantum experiment that now I want to get into some little details to understand how it works. This is the barrier. This is one valley of the washable potential I showed you before. And we are ramping the current, which is here. Depending on the current, we can change the height of the barrier. And then we know that the first process can happen is thermal activation, and which has this kind of simple dependence of the plasma frequency. Then has been, if we now, this is a stochastic process of the switch from the superconducting to the normal state properties. And this is somehow the picture of what is happening here. So if we plot these switching probabilities as a function of temperature, like here, we see something, we see some kind of characteristic dependence where, the width becomes thinner and thinner by lowering the temperature and higher the peak. But below some threshold temperature, that in this case, for instance, about 40 millikelvin, we get some kind of saturation of the width. And this means that the process is not anymore thermal, but it's happening quantum. These are some kind of, calculation by Caldera-Leggett. What is important to understand is that this depends on the dissipation, the Q factor. If dissipation is high, there is no way you can see macroscopic quantum tunneling. If dissipation is low, and it means high Q values, you can have the process of macroscopic quantum tunneling. Obviously, in order to make sure about that, DC measurements are much harder than RF measurements. And this could be noise. How to be sure it's not noise? Answered by Devoré, Martinez, and Clark, were the first one to do this experiment in an extensive way, is that you apply magnetic field, you change critical current by applying magnetic field, you tune plasma frequency, and you tune the crossover temperature. And so, like here, you change crossover temperature by applying magnetic field, and so you are sure that this is not noise, but is an intrinsic quantum effect. So we're talking about macroscopic quantum tunneling. And these are real fingerprints. So these fluctuations are a way of characterizing the phase dynamics and even stating that we have energy levels here and we have macroscopic quantum tunneling. This is a long story, and also, again, for this educational part, the first measurement made by Fulton Dunkelberger, who set up this idea of studying fluctuations. Then there were some measurements also from Bell Labs group and IBM, but with the function of temperature. But then it was set by Martinez, Devoré, and Clark a few years later with a set of experiments. It's not only the saturation. You need to do a lot of it, and you make to understand how much dissipation there is. And then also they made the first experiments about applying microwaves here and exciting the system from one level to the other one. And again, these graphs are not the first part. Then you need to make sure that there is not noise, there is a consistent way of establishing all parameters, normal resistance, dissipation, quality factor, and so forth and so on. There is another important process here that can happen, and that is phase diffusion. So if the junction has small critical current, and this means that the quality factor is reduced, you may have that the phase is trapped here. And this is important because with all junctions that go towards lower critical current values, like the one I showed you before, this is going to happen more and more, and because the barriers can be more sophisticated, and so it's something that is happening more and more. But what I want to really shortly to make you understand that this, now you can see before it was just decreasing. Now, in this case, it's increasing. What I want to tell you is that, without getting into details, that these are real fingerprints of whatever process escaping or retrapping is happening. And we are very advanced with our current understanding of that by studying these fluctuations for obviously low damping junctions, under damped junctions, to establish the phase dynamics. So here, we have these characteristics. This is the one crossover temperature between thermal and quantum. With the phase diffusion, we have another characteristic temperature where here the sigma, width of the distribution decrease, and here they start to increase. So these are some kind of clear markers of the physics which is happening. And there are also, I highlight here some of the contribution from the Pekola group in Finland and Jim Lukens, who first measured that. And this was also measured before in the Esteve and Devoré for junctions with very small critical current, but some kind of same physics with slight differences. And recently, we also did some kind of, by using high TC superconductors, here, just to appreciate that here is not decreasing some kind of saturation. Here just meaning that we are so accurate that we can even tune crossover temperature between quantum and thermal and between phase diffusion and thermal. We can change them. This was made by using some tricks with the capacitance of the high TC superconductors. And so we can somehow build a very nice dissipation map, and we can place the junction in this diagram, and by understanding the Johnson energy and the temperature, we can map them and understand the physics. So this just to prove how we are accurate, and even in the high GC regime, like here, for these junctions, we have high critical currents, and what I'm going just, again, here just to prove the principle, is that these apparently may look as those before. You have decrease and then increase. This is the distribution profile, and here you have as a function of temperature. And actually, when you have very high GC, the physics not anymore ruled by the phase. So this means that in these cases, we did exact fitting and detailed studying. What is going is that some kind of phase leap mechanism occurring, and there are hints of different non-equilibrium dissipation modes. So this may mean that this means that these are different processes. So if you have a switch in this junction may be different temp. Okay. And so some experiments need to be, you need to understand what kind of switch is the one below. I try to go, I will go faster, and I take advantage of the talk of Jacopo Santamaria yesterday about ferromagnetic junctions, so I don't need to introduce anything about triplet superconductivity and why these junctions are very nice. What this again have been explained yesterday. What I want to point is that we need also here to understand phase dynamics. There are some kind of preliminary or some all works, and actually we have done, this is another reference from a group of Tübingen, and basically what we've done on the junctions of Mark Blameyer that are ferrinsulator barrier, gadolinium barrier here, with niobium nitride. We have performed macroscopic quantum measurement. We have confirmed that this junction, even if they have some kind of active magnetic barriers, they can be they have a clear phase dynamics, they have macroscopic quantum tunneling, and so they have all prerogatives to be inside the quantum circuit. This also characterization of all these phases of subgap currents, and we are sure that all these junctions are very are ideal from this point of view. About triplet superconductivity, there are a lot of experiments. The main idea is that, as Jacopo explained yesterday, if you observe ICRN for a long depth, this means that only triplet can survive. We have, and these are some kind of relevant works on the topic. What we have done also is an alternative way, and this is, again, on this spin filter junction, by measuring properties at very low temperatures. We have seen very anomalous behavior, and this flat area here is some kind of demonstration of triplet. Yesterday, Davide gave an extensive talk on these aspects. But again, here, this particular behavior characteristic of this phase transition. And we also built some kind of map of this temperature dependence playing on the impurity levels inside the barrier. I'm going to the end. I will jump something. Something very nice is also the possibility of hysteretic behavior. So the magnetic pattern shift because of the ferromagnetic behavior here. Here we started with gadolinium barriers, then we have also tried permalloy, palladium ferrum in a different types of junctions, hard ferromagnets, soft ferromagnets. And we also have seen that by applying microwaves, we can have some kind of tuning, so we have for the same magnetic field two different critical currents. And this is somehow the proof, the principle, I'm going fast here, so by applying RF pulses, that we can tune these two-level junctions here with magnetic pulses and with RF pulses. And this is the idea which is behind our proposal of replacing inside the transmon here the traditional junction with a ferromagnetic Johnson junction. And this is the paper which recently appeared. And actually here the main advantage is that you don't need to apply a bias line, but it's enough, transmon itself, and you will have you can tune the Johnson junction just by applying magnetic pulses or even microwave pulses. And so this works as a qubit sensor. And we have all simulations, and also we have a very important first technological step. To have this kind of hybrid junctions, it's convenient if you want to have complicated setups and, some in the direction of mixing quantum platforms. And I arrived to this one, and then I'm set. That is an important technological result. We have basically extended the ferromagnetic junction to aluminum technology. Again, we have very beautiful Johnson junctions. This is done with Carmine Granata and Antonio Vittoliere. We have perfect junctions, this is figure met, and we also have the typical, in this case, is inverse proximity effect shift of the magnetic pattern. Actually, in this case, we have basically changed the thickness in order to be in this regime. So we have Johnson junctions, we take advantage of underdamped behavior with a ferromagnetic junction, which can give the ferromagnetic behaviors. And this is important because it's the first example of aluminum technology with a ferromagnetic barriers, and so it's compatible with all quantum circuits. And on top of that, the idea is that you don't put ferromagnet inside the barrier, but you just put afterwards, and so you solve a lot of technological problems. I go to the conclusions, and I skip all this part about the phase, we figure out the phase detectors, and I just very last one. That I was very impressed by the talk of yesterday of Nicola Poccia, and this possibility of getting wonderful junctions. This is a great passion of mine. I go back to when we proved the wave experiments in ITC junctions, and I think that this can be a good candidate for a new generation of quantum device, without putting any limit on it, for quantum device. And conclusions. I think there is a lot of physics in these hybrid Johnson junctions, and Johnson junctions are real wonder of nature, because not only you can do quantum computing, but you can really play with macroscopic Hamiltonians. And this I didn't get to talk to you, but yesterday David did partly, to invent some kind of new devices, in particular this is a kind of new phase detectors. Thanks so much.
Thank you very much. We also have some time for questions. There is a question over there.
Thank you, Francesco, for this wonderful overview of everything Johnson related. I have a problem. Can you comment on Josephson effect in strontium ruthenate? Because for quite some time it considered to be as unambiguous proof of chiral P wave. Then there was this night shift story, and nowadays people say no, it's not chiral P wave, but ignore data of Liu and companies. So what is
in private? My point is that for some claims you really need some kind of solid background. You need to do a lot of statistics. You need to wait to say a few things. And so that's my opinion. Some are clear. The technology behind is amazing. They are amazing. Sometimes some claims can be a little bit behind the step because there is still something to improve. And this I've lived on my own with ITC. In a few years there was an amazing improvement, and at the end we were thinking that there was some effect that were not there, and then you have to wait and to see that. I would say that we say in Italian, tempo è galantuomo, time is a gentleman. And so, but my point is that it's very exciting to see so many different types of Johnson junction with so much physics and with so many possibilities. And all these junctions are really a demonstration of the power of the field. Thank you.
Okay, there's another question over there. You already have the microphone.
I'm not expert in this, so maybe this will be completely uneducated comment, okay? But I think that maybe your search for, the search for Majoranas, which you mentioned, is maybe too narrow for this kind of possibility, because if you have a possibility to make a quantum electrical circuit, which you design yourself, then I would somehow look for creating whichever topologically protected state I can make. Why Majorana? I mean, I would really, this is exciting to me in some sense, but the possibility of putting in maybe some, I don't know, maybe some reflections in the waveguides that would create topological twists and so on. I mean, it seems to me you have endless possibilities. Yeah.
I completely agree with you. That was the sense of the talk, just to give this, the feeling of this amazing opportunity. About Majorana, I would like to say that I'm at the head of that. You know, there are some groups which are really doing good research, and for sure, you know, everybody has to be careful about the conditions of the experiments, you know. But is an example. I would say I completely agree with you about the final target, that we have an amazing system. But in the meanwhile, if we can prove other things like Majorana or whatever, they are very welcome.
I'd like to use the opportunity for a last question. 15 years ago, I did some experiments of classical circuits based on normal Josephson junctions and pi junctions based on a D-wave symmetry. And at that case, the junction properties were quite different. And also for our ferromagnetic junctions, the dynamic properties are different. So when you can have this wonder of nature, as you call the Josephson junction, what is the perfect junction you would imagine, or the perfect pair of junction, maybe conventional and pi junction, what you would imagine if everything is free to choose?
You know, I think it depends on the final application. Really, that's the final. You know, again, what, you know, I have a long story on ITC, and it's still my first love. and then we are getting so much into ferromagnetic junction. They are really wonderful systems, and they are very flexible. So again, as an example of the application of this idea of the ferrotransmon, that's the name we call this kind of transmon with ferromagnetic junctions. You know, in principle now, no, we are not thinking of replacing the transmon, you know, to go in the IBM computer. But what I think is nice is to believe that to have more tools, you can have different platforms, and may be convenient to interface with another platform, and that specific junction can be useful. So that I would say that you have to see, you know, I would take advantage of the richness of the field and the possibility of having different barriers for different aims. Obviously, if you want to have a superconducting transistor, which is always the ultimate gate, you know, Nobel Prize, the first who will prove it, you know, you want a semiconductor as a barrier. There is no, and so you work on the interface.
Okay, thank you very much, and thank you again for this brilliant review. I'd like to hand you this, and then we close the session.
Thank you. Thank you.
So the further session starts at 10.
It's my pleasure to invite the first speaker, Ahmad Awad from the Gothenburg University, Sweden, for the first talk entitled Synchronized Spin-Hole Nano-Oscillators Arrays Based Using Machine and Neuromorphic Computing. So, Awad, please, floor is yours.
Thanks, Alexander, and also I would like to thank the organizers and also Professor Aliyev for inviting me for such a nice conference and nice place with nice weather. So I will not talk anything about cryogenic magnonics. So basically, it's slightly off the scope of the session, but I'll present to you, I think, interesting talk about our attempt to do non-conventional computing using spin-hole nano-oscillators, and that based on synchronized spin-hole nano-oscillator. What we do, we will try to present like neuromorphic computing and I-sync machine based on those devices, and this work was done at Gothenburg University in Hall. In collaboration with Johan Ackerman, that is my previous postdoc post, and partly in this PLS microscopy facility at Gothenburg University. So the outline of my talk, I will motivate why we need non-conventional computing and why we use spin-hole nano-oscillator for this, and then I will show you the mutual synchronization in arrays and in 2Ds and how those can be used for neuromorphic computing. Then I will introduce our approach using spin-hole nano-oscillator for I-sync machines, and then how to control them individually using optical techniques, and also to read them fast using the optical techniques. So basically the motivation is still the same. So we want to make computing that mimics the human brain, for example, like with the artificial intelligence. Probably the first attempt is back to the 50s with Rosenblatt perceptron that was based on neural network, all-to-all connected, and with the promise of basically mimicking the sense and recognize as a human. You know, the idea behind this machine was to so Rosenblatt was a psychologist, and he wanted to build a device that can basically recognize cats from dogs. This was inefficient, but and the research in this area had faded, and it was focused on software and algorithm till recently, and the recent revival of this basically motivated by the same that, oops. So motivated by the same that we need the artificial intelligence to do some problems that it's difficult using the traditional computing. Also, we are moving toward IoT and smart cities, where we need basically to do purposed computing on where we need basically to do purposed computing on the sensor or device, camera or pattern recognition, then transmit lesser data as the data that and all the ICT information and communication technology will consume approximately 30% of the total energy produced by 2030. Also, the robots, autonomous vehicles is already here, we know. So we need to do this in alternative to von Neumann architecture that consumes a lot of energy and it's relatively at low frequency, and we need something that it's scalable, small, and time and energy efficient, and basically we think that Spintronic has promised to do this, as it's fast, it can work in different frequencies, consume less energy, and it's wave-based. Now, why we need oscillators, this spin-hole nano oscillators? So we were basically inspired by two works. The first is the seminal work by Gruyère group of vowel recognition or pattern recognition using oscillators. They use 4 oscillators to and see the injection lock-in pattern that can mimic the patterns of vowel, and this I will explain later. So this was first work, and the second work is that oscillators can be used as icing machines that solve hard problems in computing, like combinatorial problems, optimization problems, and etc. And those can be used in large numbers and can have a very high number of variables. For both those approaches, we need injection locked coupled oscillators, and for this, so we need nonlinear oscillators, and this we have, and I will show that we can have the rest of the ingredients to have high density neurons and low power consumption, and the possibility of to synchronize, or at least a highly coupled system. So just as a brief introduction to the spin torque, or the oscillator-based physics. Basically, the magnetization is precessional damped motion that described by these two first terms, and the third term is basically the spin transfer torque that contract the damping, so basically can get auto oscillation, and this auto oscillation then can be read through like magnetoresistance, GMR or TMR, or like anisotropic magnetoresistance. And in our case, for the spin hole, we use basically the polarized spin current. We use pure spin current produced by the spin hole effect in heavy metal. When you pass a current, there will be a deflection of the spin in different direction, and the accumulation occurs. So if you have a ferromagnet in the vicinity, you will excite those auto oscillation with this spin transfer torque. And there is different geometries from those devices based on how you want to concentrate the current and read out the signal. And those had been reported by different groups, from Cornell to Demokritov and Krivorotov. And our interest was mainly to reproduce these devices, that nanoconstriction-based spin-hole nano-oscillator, as we think that those are the most interesting, as they are easy to fabricate, they dissipate well the heat with their planar geometry, and they have optical access, and so simple, and probably will lead us to do simpler physics and to understand things more thoroughly. And we did this based on the first, so the first publication was by Demidov and Demokritov, and this work, they show this nanoconstriction devices. You concentrate the current here in a small region, and this will provide the magnetization auto oscillation, and this signal will modulate the magnetoresistance, and you can read it electrically and from the BLS. And the signal here with M-plane applied current, you can see that it has a negative frequency shift, that it's this redshift due basically to those modes are localized modes, and those localized mode and the vicinity on the nanoconstriction get more localized with the current. Now we wanted to use those, but in a different geometry, so we apply an oblique field. With oblique field, you get more extended mode or propagating mode, so you basically contract the nonlinear frequency shift. And with this oblique field, we get this non-monotonic dependence when you have red shift and blue shift, and this is a sign of extended or propagating modes. We published this and more details more recently for different constrictions, and you can see here the power of those oscillators is very small, and the line width, it gets to very narrow line width, but still not good enough for applications in signal generators. So the modes here in this region are of our interest. Why? Because those out of plane angles, we can see that the modes start to extend. So if we put another nanoconstriction, there is a good opportunity for those spin wave to interact through their tails. So we used those conditions, and we put another oscillators, so now those can interact and talk to each other and synchronize, as we see. So here those, each signal of the non-oscillator, and then they synchronize at this point with their power enhanced, and they have one signal. And we could do this first work at Nature Physics. We could do up to 9 oscillator at one chain. We can see that their frequency gets synchronized above a certain current, and we can measure this also with the Brillouin light scattering, the PLS. So we can see the spin waves. Here, this is a 2D map of those oscillators. We can see that all of them are active and functioning at this single frequency. Also, we can see their frequencies as a function of the position, and we can see that all of them are working at single frequency. So then we moved on to do it in the second dimension. So we just added on a neighboring array, and we did this up to 10 by 10. Back then, we just get the full synchronization up to 8 by 8. Now we get up to hundreds and thousands. But with this, basically, we get fully synchronized oscillators that they are highly coupled, and their characteristic shows approximately what's expected, low line width, and they are high frequency, so the Q factor is high, and the power enhances with the increased number of oscillators. And here for this sample, we have 4 by 4 oscillators. We can see that they have 4 signals that synchronize in one. And if we do this optically, we can see at the unsynchronized state, we can see that those basically the parallel chains synchronized first, and then here we can see those, the lower frequencies and the high frequencies. And then at the synchronized state, we also see that those are, all of them are synchronized and working. So we could do this. Then we get here to the point of the computing. So the work from Grolier group, where basically they used vortex-based nanopillar oscillators, and those have magnetic vortex that oscillate at megahertz up to 1 gigahertz. So they are, let's say, relatively low frequency. They can produce high signal due to that they are based on tunneling junctions, so their signal can be really high. So they can be electrically synchronized between each other from one to another. They are individually connected, and there is a microwave stripe over them. So if we pass an RF current over this strip, we can basically inject lock those oscillators. They will adjust their frequency to this external frequency. And if we start with this, we have those 4 peaks of the oscillators. So we start injection locking, and you can see that there is distinct regions where you have one oscillator or more that are synchronized. So this is the injection locking map. And from this map, one can basically tune the oscillators to match a pattern that he wants to classify. And in this case, it was vowels that basically was coded in this, and those 2 frequencies. And one can basically map those vowels to totally separated regions, and one can do by this recognition of pattern, vowels, etc. So this was nice and great work, and our thought that we have much higher frequencies in our oscillators. So why can we try to do this with the spin Hall nano oscillators that are much simpler, much more compact, as they are basically done through lithography on one device. And we tried this. So we tried this with this 4 by 4 oscillator, and so we lost we have the 4 by 4 oscillators. So we have the signal. So similar to Grolier, we have those now as one oscillator. So each chain will behave as one oscillator, and we will try to inject lock them. Now we cannot do like with the stripe. So we just inject lock those with the same RF that it's running on the sample, and we do this. So they have now first neighbor interaction. So those neurons, they do not have a global interaction. Actually, they have till a certain point due to the dipolar interaction. And what we see that here, if we take one frequency scan, we can see that those can be synchronized at different regions, and we can get the same type of map now at very high frequency. So this is half of the frequency, as we can inject this at the second harmonic, so it's parametric injection. So those approximately at 19 gigahertz. We can tune those frequencies, of course, by current, as we see, so we can change this pattern and we can change this by field also. But we want to do this also like individually to have more control or phase control over those. And we will see this later, but let's hope to the icing machine, and first let's present what type of problems that those machines are most adequate for. So basically, there is a computational class of problems called non-deterministic polynomial time problems, which require like increasing time, there is no efficient frame of time or resources to have a solution of those in computing. And one simple example of those are like travel salesmen or postmen, that you need to go through different cities without passing the city. So this is the constraint, and return to the same origin. What's the shortest pass? So the possibilities can grow really very fast. Here we can see with 5 cities you have 120 possibilities. With 32 you can get to 10 to the 35, so possibilities. Other examples of such problems, face recognition or pattern recognition, like in simulation protein folding, also like in epi an issue when you need to find the global minima of your system, in financial prediction, social networks, etc. So there are multiple problems of those types that they are very difficult to, or impossible to solve in the traditional computing schemes. And basically there was, just I will present this, that there is the icing formulation that based on the icing model had been predicted to be able to solve all this non-polynomial, non-deterministic polynomial time problems, even the hardest of those, like MP complete and MP hard. And this we have the carbs, like those he predicted 21 problems that it's impossible to find solution in efficient time or resources. But here there is a review of all the predictions of algorithm that basically adapting those problems to the icing formalities. And the icing machine, basically, that you have an icing problem that you can map to the icing model. So icing model is the 1D model presented by icing that with interacting spins, and then by Onsager that he presented this in 2D, and then the most generalization would be the spin glass. But it keeps the name the icing model, where you have a spin system that interacts with J, and you have like a Zeeman term here, like external field. So if you can, using those formalities of the icing formalities, basically you can mimic any problem to this icing model using spins. So you need a system, then the physical system, basically that can adapt to those spins and to the interaction between those spins, that can be optical parametric oscillators, quantum bits, or any other oscillators, and those basically you give energy annealing, and they will give you their states that would be basically the solution. And this, if with the von Neumann computing, you need to basically pass and see the energy at each level, or use some software and algorithm to basically mimic this. But from the icing machine, the physical system will go to the global minima, and I'm running out of time probably, so I will go rapid on this. So there is just going to quantum and superconducting, so we have the D wave based on squid and Josephson junctions, so that based on the current direction that mimics this spin, and this is a commercial available system that you can simulate any problem on this D wave system. The latest one is the D wave advantage, and it has a lot of qubits, and they are highly interconnected. It's working in dilution and consume a lot of power, and it's a massive device, and it needs quite some time to reach the solution. Of course, it has the quantum advantage of tunneling between states, but maybe not so much advantages over other things. But there is an approach that presented by Wang, basically that he used off-shelf electronics to do oscillators, basically ring LCR oscillators. And he started doing this with 8 to 32, 64, up to very high number of oscillators. And he did I-sync machine with those, and we were inspired by this. So this is the actual photo of those. And what he can get, so he can get faster than the GPU computing with just this ordinary electronic and with this 1 megahertz operating conventional electronics, and the prediction that you go to higher frequencies and you can basically lower the frequency down. So this is what we hoped, and now this at oscillators, basically how you can present the spin. It will be presented as basically the phase of the oscillation. So, and to do this, so you go from your I-sync formalities, so to the spin hole non-oscillator, for example, and you inject at parametric at the double frequency, and then the oscillator, each oscillator have the freedom to basically to inject at 0 phase difference or at 180, and this would be kind of the binarization, and this just dissipated here. So if you inject at the second harmonic, so it will be equal to the oscillator to be injected at 0 or 180 degrees, and this is, so we've binarized through the phase. And of course, if you inject on the same frequency, you will have the typical injection lock-in, and you will end up at 0 phase difference at sufficiently high power, of course. So we can do the injection at the second harmonic, and we can get this with a single oscillator. We can get very nice injection lock-in bandwidth. And to do this on oscillator, it's the same. So we have 4 oscillators, so those are interacting and can have 0 or 180 phase difference to the external frequency, and with this we can binarize. So first we do the electrical measurement, so we inject lock an external frequency we increase the power, and we can see that the oscillators start to inject lock at a certain power. This is due to the noise in the system, the thermal noise. But then we can see in the injection lock can have like different power levels, and this is what we assume, that due to the different states of the oscillation. So here we have 2 oscillators, so they can go in phase or can be anti-parallel or to each other. And then we can see this as a function of frequency, that it's the same thing, that we can go from one state to another, and like from parallel to anti-parallel. So then how to resolve this phase? Actually, we can do the phase resolved PLS. It's kind of Mach-Zehnder. We can modulate the light at the same frequency of the injection lock-in, and we can see the phase. So here we have these 2 oscillators, and here we have the 2 states. Here we can see the one of them at one phase and the other, and here we change the phase, just the global phase shift, just to be sure, and we can see that they are like anti-parallel. Here we can see that they are parallel, and we got this phase binarization confirmed. And we can do this with more, like here we have 4. Oops, I just go one step. So here we have 4. We can see that we have 3 states, A, B, and C, with A higher power and B no power and C like intermediate. And we do the same. So here we have the measurement, and here the repetition with another phase shift. So we can see that we have like this antiferromagnetic coupling between those, or so we have 2 spins up, 2 spins down, and this will make zero electrical output power. When all of the phase is equal, we can see that they are parallel, and all the SH nodes have the same phase. Here, if we just present like points between those, so not take the whole map, so we can see as function of the phase. For the C case, we can see like we have one of them that it's going against the phase of the others. So with this, we could have like most of the ingredient of the spin hole based icing machine. So we have a system that can be basically binarized, and we can have the optical readout. Of course, from Ackerman Group, basically we have published two articles based on like electrical control of those with voltage control and with memoristive control over the current. I'll not go into details with this, so we'll just keep this with the optical part, so we can do the annealing, so the computation, we can do the annealing through the current or the field, and we can read those out, and the problem, as I mentioned, that can be solved. Now, if we want to tackle this optically, so we showed, yeah, I have no time, I will just lie. So I will skip those. So we showed recently that we can control those optically through the laser, so we can change frequency of the oscillator through just laser heating by one of those, and we can rapidly also read the phase of those using FRMOC here for 2 states, and this is like repeating also the spatial resolvence or the optical spatial resolvence. So we have also like optical control over the oscillators and read the fast readout of their phase. And with this, I will come to my conclusion, and thank you for your listening, and thanks for your patience.
Thank you very much for your impressive presentation, which is now open for discussion. So please, yes, Andres Line, please.
Ahmad, of course, your work on synchronization of many oscillators is very well known. And my question is the following. In one of the slides, you've shown that now you get a pretty significant power getting out of it. Did you manage to switch from anisotropic magnetoresistance to tunneling magnetoresistance as a mechanism of extracting power, or not?
Well, we are getting significant power with this AMR, and we get now like higher numbers. But with the TMR, I'm not involved in this part of the fabrication, but there is very nice development we have collaboration with ONO group, and we are doing locally fabrication of MTJs. It's slow, but it's getting there. So we have now yeah.
Because if the TMR problem will be solved, that will be a very big advance. That will mean that we can actually use spin torque oscillators in conventional systems like phones. Because you've got the line width of about 1 megahertz. If you will be able to get at least 1 microwatt or 10 microwatts from a single device, that will be sufficient to start producing it in millions.
Yeah, exactly. Yeah. So but we get down to 170 kilohertz of line width.
Yeah, my second question is, what is the current density in the synchronized systems? And did you try to drive the synchronized systems for a long time, say a couple of days, without switching off?
Yeah. So the current densities is typical to the oscillators regime. I think we did not calculate, but it should be like 10 to the 7 ampere per square meter, square centimeters. The thing that with the synchronization, if we can go rapidly, yeah. So with the PLS map, for example, with the 2D map, so this map took 2 days, and there is no practical, yeah. So, and this is with DC current. You imagine with the pulses that you will not have any effect. So this can be considered like a very long time.
Thank you.
Yeah.
And my last question is of a principal importance for computing. You know, spin torque oscillators, they look nice, but the energy efficiency is bad. You need milliwatts to drive it, you get nanowatts of output power. So if you will use a lot of these devices, there will be a huge energy loss. And do you have the answer to this question? Because it looks well on paper, but in reality you have, you use only at best 1/1000th of the spent energy. Thank you.
Yeah, you are totally right. But this, if you think that you are taking energy out of those, but at least for now, I'm not trying to think that we are trying to convert this energy in useful way. So if we just want to use those in computing, so those fulfill the consumption necessity, like the energy spent per oscillation as they get very high frequency.
Finally, I would like to make a short comment. I think that this group is really the closest in the world to real success in terms of mass-produced applications. Thank you.
Thank you. Thank you.
Okay, so we need to move ahead. It's my pleasure to hand in the certificate of attendance to Ahmed Awad.
Okay, and we have to continue the program. So the next talk will be given by Mikhail Selay from Tampere University, Finland. And the title is Anderson-Higgs mass of magnons in superconductor ferromagnet superconductor systems. Yeah, please, we have 30 minutes, but please try to leave a few minutes for discussion.
Okay, good morning, everybody. I would like to thank a lot organizers of this nice conference, and especially Alexander Dobrovolsky for inviting me to present this actually theoretical talk, but based on this recent paper in arXiv. Yeah, but it is very closely connected with experiments. So partially published also in this paper with my co-authorship. So to introduce the topic, let me talk about a little bit about Anderson-Higgs mechanism of mass generation. Generally, it is well known in high energy physics, for example, for generating the mass of electroweak W and Z bosons, which is quite important in general for our universe. But historically, these ideas come from superconductors, superconductivity, and essentially was proposed by Anderson. Yeah, by Anderson, in a setup where the Higgs mode actually is the superconducting of the parameter. And this is the very well-known picture of the Mexican hat energy profile with the minimum at some finite amplitude of the parameter, and also this massless Goldstone mode, which in superconducting case is the phase of the parameter. Initially, it started from the attempts to eliminate massless modes, which naturally come from the presence of the parameter, because it gives this contribution to the action, which produces the sound-like excitations, the gapless Bogolyubov-Anderson mode. And in reality, in experiment, there was no any gapless modes in superconductors, and the solution to that was suggested by Anderson, who have shown that due to the broken gauge invariance, so this order parameter phase is coupled to the vector potential, and this gives rise to the coupling to the this electromagnetic part of the action, and produces, instead of the gapless Bogolyubov-Anderson mode, we obtain the gapped photon modes. Seems doesn't work. Yeah, so they look like flows. So there is like longitudinal and transverse modes, and both of them are gapped, but the problem is that this Anderson-Higgs mass in superconductors is not directly observable, because this gap of photons is equal to the plasma frequency, which is the same as a normal metal. So in metals, photons have the same energy gap both in the normal state and the superconducting state. And the presence of this mass shows up only, like the difference with the normal state shows up only in the low frequency response, well-known Meissner effect. When this frequency is equal to 0, then the solution of this equation is like imaginary momentum of the photons, which is the decay of the magnetic field inside the superconductor. So due to the coupling of the parameter phase to the electromagnetic field and the charge density, this mass is not directly observable for photons in any condensed matter system. So my suggestion is like this mechanism can be directly observable in case of magnons, because magnons are naturally gapless excitations. They are not coupled to charge density, they are charge neutral. And in case of this, for example, infinite ferromagnetic film without any geometric anisotropy, in-plane geometric anisotropy, and in the absence of external field, this rotation of magnetization is massless mode. And the suggestion is to place this ferromagnet in the vicinity of superconductors, and to show that this will generate spontaneously the mass of magnons. So this mode, magnetization mode, and magnons become massive. The motivation for that comes from experiments, of course. Recently there were a number of experimental observations of these spontaneous ferromagnetic resonance frequency shifts in structures which consist of superconductors, ferromagnets, superconductors and niobium, ferromagnets are permalloy, So these tri-layer structures, they in superconducting state, they produce this spontaneous shift of the ferromagnetic resonance frequency. So these are two experimental pictures from this paper. This one is the ferromagnetic resonance in the normal state, and this one is in the superconducting state. So clearly there is a huge shift of the ferromagnetic resonance, which can be described as a spontaneous anisotropy field, but there is no anisotropy. It was a puzzle, actually, for theoreticians. My goal was to understand this and actually to show that this is the actual Anderson-Higgs mass. So let me start with the qualitative picture first. So let us consider this system ferromagnetic film between two superconducting layers, and assume that ferromagnet is very thick, so that we can neglect the Josephson coupling between superconductors. And then the question is, what are degrees of freedom here? So one degree of freedom is the Josephson phase difference between superconductors, and the other degree of freedom is magnetization rotation around this z-axis. Both are gapless, as I said, in the absence of Josephson coupling and in the absence of a magnetic field. And I will show you just in a while that this phase difference, Josephson phase difference, played the role of the Goldstone mode, and the magnetization rotation played the role of the gauge field. And they are coupled and produce the Anderson-Higgs mass. So to see this, we can write the action of condensate and of the condensates, superconducting condensates in the upper and lower superconductors. It's just the kinetic energy, the vector potential, and gradients of the phases, phi1 and phi2 in upper and lower layer. And if we say that the vector potential outside ferromagnetic film in the upper and lower subspaces is given by this equation, because here is the magnetic field inside the superconductor. This is vector potential. And then we write the total action consisting of the sum of these two contributions and neglect the gradient of the total phase. So we assume that there is no global current, only contour currents in this upper and lower layers. And then we get this action which now contains this magnetic degree of freedom and phase difference. And the last step is that we can expand this magnetization rotation around a small angle and get this action which contains this angle as the in the form of the gauge field and some phase difference in the form of the Goldstone mode. So the last step is to understand where this Goldstone mode disappears, because in general, in a static case, we can minimize this term by actually adjusting the phase according to the magnetization angle. So this will be always 0 in the static. But in the dynamics, when magnetization rotates and this phase difference which is needed to compensate this rotation depends on time, it will produce a Josephson voltage between upper and lower superconductors, and therefore like this AC current, because we assume that ferromagnet is conducting layer. And the AC current is localized at the skin and the layer of the thickness of the skin thickness near the edges of the structure. So if you assume that the structure is much larger, much longer than the skin length, then we can neglect this phase difference, and we are left just with the mass generating term, which is proportional to the square of the angle of this magnetization rotation, and it gives the effective anisotropy energy, which in this simple case, which we consider this for qualitative consideration, like the superconducting layer is much thinner than the London penetration length, is given by this equation, and in principle it describes already the experiment qualitatively, but not all features. So we need like more strict theory, and this is possible to write using like standard Landau-Lifshitz-Gilbert equation for the magnetization, and Maxwell equation, which combines magnetization, rotation, and conductivity of both superconductor and ferromagnet metal. So there are some assumptions which we can make. As I said, the structure is much larger, much longer than the skin length, so we can forget about age effects. And but at the same time, it is much shorter than the wavelength of the photons. This will allow us to neglect the displacement currents, and this will lead to some important effects, as I said. But and under these approximations, we can say that all fields depend only on the z coordinate, on the perpendicular, and we have only y component of the AC magnetic field everywhere, so the system simplifies quite a lot, and it can be solved analytically. And the first result is this equation for the ferromagnetic resonance frequency in superconductor, ferromagnet superconductor 3-layer. So this is quite like I would like to say textbook problem, but it was not discussed in any previous textbooks, only like in this work. And this equation is quite simple and but interesting. So it has this usual Kittel equation, Kittel frequency contribution for the isolated ferromagnetic film, but also this spontaneous shift, which is proportional to the thickness of the ferromagnetic layer thickness, and also by this hyperbolic tangent of the ratio of the superconducting thickness to the London penetration length. So at zero magnetic external field, it gives this Anderson-Higgs mass of magnons, which is given by this equation. And if you plot the magnetic field dependence of the frequency, we see that it looks like very similar to the experiments. So numbers also coincide. We can study this dependence of this shift on this ferromagnetic resonance frequency shift on the parameters, temperature and thickness of the ferromagnetic layer, and both dependencies show the saturation for saturation at small temperatures and saturation for large thicknesses of the ferromagnetic field. So this temperature dependence of shift is approximately given by the temperature dependence of the inverse penetration length, inverse lambda. This was actually a prediction, and recently there was a new experiment which confirmed these claims that they measured the dependence on the of ferromagnetic resonance shift on the thickness, and obtained saturation, and also saturation at low temperatures like that. Yeah, I would like to stress that these shifts are huge. They are like of the order of 1 Tesla. So in frequency, it is like dozens of gigahertz. Now, okay, so this was actually basically the main part of my, so it's 5 minutes till the end of the talk. Okay. So now I have 5 minutes, and I will discuss shortly predictions, further predictions. Actually, by now I have considered only the fundamental ferromagnetic mode, but this shift of the frequency, as I said, it is just the spontaneous mass of the magnons, and we can calculate the spectrum of magnons in this system. For example, in this Damon-Eschbach geometry, when the magnum momentum is perpendicular to the magnetization, and in the normal, like in the usual case, when we have just a single ferromagnetic film, there is a well-known equation for this magnon dispersion. So it has this Kittel frequency and this like momentum-dependent frequency. So for external, so these dispersions are plotted for several values of external magnetic field here, and for zero magnetic field, this excitation is gapless, yes, as I have said before. So magnon frequency starts from 0. What happens in case if we attach superconductors? So magnon dispersion now looks like that. So it is a little bit more complicated, but there is also like analytical expression for that. And there are limiting cases for large momentum. When momentum is much larger than the inverse London penetration length, we get standard result for the ferromagnetic field. But for zero momentum, there is this Anderson-Higgs mass, finite frequency of magnons. And the most interesting thing is that we can, by changing temperature, we can change the character of this spin wave of this magnon. For example, when this spontaneous shift becomes larger than the frequency of this magnon at large momentum, we obtain the change of the group velocity sign. So this is a temperature-controlled transition from the forward spin wave to the backward spin wave in this system. And this can be studied experimentally, checked experimentally, and it also gives rise to a bunch of novel functionalities. For example, we can control magnetic states by patterning, by using the patterning of the superconducting layer, because it will produce like the barrier for magnons. Or we can control superconductors by light, by external irradiation, and this will also allow us to change the spectrum of magnons in the ferromagnetic field. so this is very useful for applications, I think. And with that, I would like to finish my talk and thank you for attention.
Thank you very much. So now this presentation is open for discussions. And you, yeah, please.
What are the typical thicknesses of a ferromagnetic film in these calculations and experiments?
It's about London penetration length in superconductors. So for niobium, it's like 100 nanometers.
Nanometers? If you're working in a range where Q, and Q is wave number, I understand, yeah?
Sorry?
Q is a wave number.
Yes. This
When you're working in a range where Q multiplied by the thickness is around 1, that means that you are working with pretty short spin waves. And you are not taking into account exchange in your dispersion laws. I understand that you are mostly interested in the gap, but nonetheless.
Yeah. So you are completely correct. So this, like here there will be exchange. So the uprise of the magnetization like dispersion curves due to the exchange effects. Yeah. So, but so exchange, but like to be like within the limits of my calculations, we need the exchange length to be shorter than lambda, than one length.
Please, any other questions or comments?
If not, maybe I have one. So it was very interesting that you have grasped the main feature observed experimentally in the shift of the ferromagnetic resonance frequency and the superconducting penetration depth, so magnetic penetration depth, enter the equation. My question is, did you compare with other materials where you can have a different lambda for superconductors? For instance, for typical materials in the duty limit where lambda is large, can you make some prediction already you have compared with experiments? What would be prediction regarding the shift of the ferromagnetic resonance frequency?
Well, this yeah, so this equation is quite universal, I think. So one can insert just any lambda here. Just we need to have superconducting layers not much smaller than lambda. So if lambda is small, yeah, we have this limit. So this limit, which I like shown in the beginning, when so yeah, so if the thickness of superconducting layer is smaller than lambda, so we have suppression of this effect.
Okay.
So
okay.
Yeah.
So basically, it's interesting because exactly in the duty limit we experimentally didn't observe too much variation of the ferromagnetic resonance frequency, but that lambda is huge in comparison with the film, superconducting film thickness. So just
yes,
also,
yeah.
okay.
And yeah, there is also important thing about like this interface between between ferromagnet and the superconductor. So if there is an insulating layer in between them, so like for example we place some oxide layer between ferromagnet and superconductor, then it will other part of the story.
Okay, thank you very much for this comment.
Thanks.
Okay, so.
Okay, we have to continue. So the last invited talk of this morning session will be given by Carmine Atanasio from University of Salerno of Italy, and the title is Quasi-Particle Relaxation Times in SFE Heterostructures and Microstrips. So you have 20 minutes.
Okay. Yeah, you should change presentation, I think. Okay, thank you. First of all, I would like to thank Alexandre for inviting me here to give me the possibility to present these results that we have obtained on study of IV characteristics, non-linearity in IV characteristics in several systems and superconducting systems. We used actually this study to make some prediction about the possibility to use materials. The idea was to make prediction to use materials as superconducting single photon detectors, actually. Okay, so it's better know that I will not go into details here, that high velocity of fluxon in superconducting materials is a very important topic also from fundamental, from applicative point of view. Alexander tomorrow will give will give a talk, I think, on magnonics, spintronics, and fluxonics. But here, the idea, as I said, was to study the fast dynamic of fluxons to determine the mechanism which, plays an important role now in superconducting single photon detectors where they are, let's say, they have micrometer dimensions. Also, in the case of superconducting nanowire single photon detectors, which are completely based on a different mechanism of detection, let's say the main important point is related to the electron phonon scattering length, which is related to electron phonon coupling time tau 0, which is, of course, not directly connected to the time, to the quasi-particle relaxation time that we measure, we detect from IV characteristics, from these instabilities in the IV characteristics, but the scaling between these two quantities it's quite robust in the sense that low values of the inelastic scattering time will typically give low electron phonon coupling time in the material. Okay, so from the instability, from the study of the instability in the IV curves, we can have information about the critical velocity of the vortices V star, which is related to this time tau e, which is the inelastic relaxation time of the quasi-particles. And from these numbers, we can make some prediction about the possibilities, I said, to use materials as superconducting quantum single photon detectors. Also, the temperature dependence. We should be trained before. Okay. Okay. So let's go here. So also the temperature dependence, as I said, will give us of tau, will give information about the mechanism which is in play in the dissipation in the quasi-particle vortex, in the quasi-particle relaxation time. So if the interaction is mainly due to electron phonon, tau goes like a power of -3 with the temperature. If in the case of electron scattering, the dependence is more exponential. So from these two temperature dependence, you can also understand what's going on, what's the main relevant mechanism of dissipation in the quasi-particles. So here, okay. So all the results which I will present here, I mean, a very easy system. So all the films and the systems have been deposited by UHB sputtering system, and also the geometry is very simple. So just order of 10 micrometer wide strip, and the thickness of the sample of the films goes between 10 and 30. Sometimes they are thinner, but I will show. I mean, I will explicitly say when this is the case. Okay, so I want just now to start from the end. So in the sense that this was some final results that we obtained some years ago on a new materials, which is niobium rhenium. These are the only films which are around of this non-centrosymmetric superconductor, which we started to use for different purposes. But the most important features of this superconductor is that it has a very short coherence length of the order of 4 nanometers, which means that you can have quite high TC also for very thin niobium rhenium films. In our case, we get something around a bit higher than 5K for 3 nanometer thick films. Also, the resistivity is quite high. So already these two characteristics makes this material appealing for superconducting single photon detectors. So, but the question that we asked ourselves was, what is the critical velocity? So what's the time, the inelastic relaxation time connected, which associated to this material? And actually, you see we end up with a quite high 1 kilometer per second critical velocity, so a tau, an inelastic scattering time which was of the order of 200 picoseconds. So, okay, someone in Delft read this paper, and they say, okay, maybe we can try to build real single photon nanowire superconducting single photon detectors. They did, and the results were quite encouraging. This is the experiment was done on 8 nanometer thick films, and let's say what was nice for us that the time, so especially the recovery time and also the time jitter for this system was quite low, and they were comparable to other performances that have been obtained on the materials which were very very established material for superconducting single photon detectors, like niobium titanium nitride or amorphous tungsten silicide. So even though the two times, as I said, were not directly connected, this was for us a good indication that we were going in the right direction. Yes. So also, this is still unpublished, the results, very recent. Maybe this is even more important because this experiment have been done on the niobium rhenium thin films of 4 nanometer thick on a white, so this is a microstrip superconducting single photon detectors, and you can see here that we have been able to detect single photons. So I say this for us is much more important because this is a very easy geometry. So I mean, you don't need to go to Delft to convince people that they have to do very, let's say, advanced things. So this is for a study of feasibility. It's for us is very important. And as I said, there are still unpublished results. So this is the beginning. So we started, let's say, 15 years ago, and we started to measure these IV characteristics, so this sudden jump in the IV curves and of niobium, which is okay, the material that we know very well, and we asked ourselves what is going to happen if we put a ferromagnet on the top of the superconductor, and we started with put the, let's say, the stronger ferromagnet iron, and actually didn't happen, nothing. So we made, we measured a lot of samples, a lot of bilayers, niobium iron. We changed, here is a 40 nanometers iron and 25 nanometers thick niobium, but we changed a lot of thickness, a lot of combinations. We always end up with the same critical velocity. Maybe this can be due or bad interface transparency between the two materials, or also to the fact that the superconductivity, the penetration depth of the superconductivity in the iron is very, very low. So actually you always probe only niobium. In fact, also the temperature dependence of tau is exponential, like was, the feeling was that you were just measuring the properties of niobium. So then we say, okay, let's change the ferromagnet, so the strong ferromagnet, and we go to iron nickel, so the permalloy, and in this case, the results were much more better. You see here, we measured a critical velocity of 2 kilometers per second, and these are two samples, 10 and 20. Okay, niobium is always 25 nanometers, and permalloy is 10 and 75 nanometer, more or less the same value of the critical velocity. Here was the saturation, more or less the field when the critical velocity saturates. And from the value of V star, we can have some information, as I said, on tau E. And in this case, tau, as you see, was 40 picoseconds. So, encouraging at that time was an encouraging result. In both cases, the temperature dependence of the relaxation time was exponential. In the case of niobium, okay, this is tau here, the factor m here equals 2, as it should be, because niobium is typical BCS superconductor. In the case of permalloy, we have also an exponential behavior, but with m equal 1, so a sort of reduced gap in the average. The system experienced the quasi-particle reduced gap in the system. And maybe with respect to the niobium iron, we have, of course, a smoother decay of the order parameter in the permalloy, because the penetration of the superconductivity is longer, because permalloy is, let's say, is strong, but it's weaker ferromagnet with respect to iron. But still, the superconducting, the coherence, the penetration depth of the superconductivity in the ferromagnet is very small, 1-2 nanometers. But here was what I think was most interesting results on permalloy. 10 years later, we studied the influence of the magnetic configuration of permalloy on the critical velocity. So we prepared 3 samples which were characterized by different different magnetic configuration in the permalloy. So one which was whose thickness was similar to the previous one, 50 nanometers, so in which the magnetization is always in plane, and other 2 which, I will not going into details here, but in these 2 cases, the magnetization as a component out of the plane, so which is going up and down, so stripes develops in the system, and we measured the IV curves in the 3 cases. Here is the critical temperature. The critical temperature is the critical current. The critical current is almost the same for the 3 samples, but what we got was a completely different situation for the critical velocity. And here, these 2 red curves are the most important results, I think. First, very high value of the critical velocity, something about 4 or 5 kilometers per second. I should also say that in this case, niobium was deliberately fabricated as a dirty, this niobium was dirtier than the previous one, so also this maybe plays a role in the, not maybe, this for sure plays a role in increasing the critical velocity. But as I said, the most important thing is the result is this. These two curves are, the red ones are measured on the same niobium permalloy bilayers. This is 200 nanometers thick. The red points are when the sample is in the homogeneous state, and here is when stripes are created in the systems. And you can see that you have an increase of the critical velocity, so a decrease of the time relaxation time, which is clearly related to the inhomogeneous nature of the magnetic configuration. Because, I mean, since JC is the same in all the hybrids, we ascribe this behavior to the different magnetic configuration, which here is homogeneous, and here is homogeneous, and here is inhomogeneous. And you can see here that we have relaxation time of the order of few picoseconds. I will not go into details. We made a lot of other, study a lot of other materials. Now we pass to weak ferromagnets, niobium, palladium, nickel. For example, here is critical velocity for niobium, and here is for niobium, palladium, nickel. And again, increase of the critical velocity. All these samples are always prepared in the same deposition run. So, I mean, niobium, the quality of niobium here is exactly the same than here. And you see, higher critical velocity. Well, this is the mechanism. Okay, also the same with, this niobium copper nickel. And again, this is niobium and higher critical velocity for niobium copper nickel. And in niobium copper nickel, the critical velocity is even higher with respect to niobium to palladium nickel, because they are both weak ferromagnets, but copper nickel is more disordered and his resistivity is higher, and this gives us a critical velocity which is higher in this case. Also, the relaxation mechanism is completely different, almost constant value of behavior of tau as a function of the temperature, which is also could be interesting for superconducting single photon detectors, because then the relaxation time is more or less fixed as a function of the temperature, so they can operate more or less. This is at the same temperature. Also we this with the niobium nitride copper nickel. This is a more complicated, let's say, layout of the sample that we measured. We have these phase leaps here, but we just concentrate on the first jump at lower current, and we also obtain the same result. So as I say, you see here, this is, yes, again, niobium, nitride, and higher velocity niobium nitride copper nickel. So when you put a ferromagnet on the top of your superconductor, we always see an increase of the critical velocity. And this is just but now what we want to do now is what we have done now. It was, since we obtained, real single photon superconducting single photon detectors have been made out of niobium rhenium, both nanowire and micrometer strip single photon detectors. We want to propose now what happens if we put copper nickel on the niobium rhenium. And then we fabricated these bilayers, we measured critical velocity, and you see here again that the results are very encouraging. So the critical velocity is more or less, 2 times of in the case of niobium rhenium copper nickel with respect to the niobium rhenium, and also I think more, maybe 4 times. And also the relaxation time is, it's 1 order of magnitude smaller. So I think I should end up with the conclusion. Yeah, we have done also, okay, now this is also interesting. I think we also spatter different materials, so niobium, rhenium, nitride. So also these are the only few, these are the only films which are around. So the idea was to make niobium, rhenium even dirty. So, say follow the same route, niobium to niobium nitride, and going from niobium, rhenium to niobium, rhenium nitride for detectors. But in this case, we did not see, at least until now, an increase of the critical velocity, or a decrease of the inelastic scattering time, which is almost the same as a niobium, rhenium. Okay, we have done different experiments. So I have shown just an overview of a lot of materials combination, superconductors, strong, weak ferromagnets, niobium, rhenium, and what is good for us is that finally detection experiments have been really and concretely performed on superconducting narrow wire single photon detectors and microstrip superconducting single photon detectors made out from niobium, which confirms our prediction. Of course, our plan now is to go into the direction to do something which is a hybrid, which contains a ferromagnet. So we want to propose to make some detectors with niobium, rhenium permalloy, or maybe better, I think, niobium, rhenium copper nickel. Okay.
So this presentation is now open for discussion. Thank you for your presentation. Are there any questions, comments?
Yes, please.
Yes, I'm sorry I missed the first couple of minutes. What is your method to determine the timescales? Because you're not doing any ultra-fast spectroscopy in real time, etc. Right?
Yeah, the message is very easily, with a very easy experiment, you can have indication about the possibility, of course, to use materials, just as a first check, to use materials as possible candidates as superconducting single photon detectors.
No, but the question is, how do you estimate the time scales? 5 picosecond, 20 picoseconds. How do you do that?
From the Larkin-Ovchinnikov, yes. Okay, from the Larkin-Ovchinnikov, I measured the critical velocity, and from that formula I get out from, yes.
Okay.
That's all.
Okay.
And I said that, of course, there are completely different mechanisms, whatever, but the scaling between these two times is quite robust, at least in our experience. And you can have indication. In fact, from Delft, they just saw this paper and say, okay, let's try, and it worked. Of course, I should also say that in the experiment of Delft, they did not optimize the electronics, they did optimize the geometry, they did not optimize the design. So the numbers that they got, they were not ideal, I think. They can go ahead, but of course they do with the niobium nitride, niobium titanium nitride, and they don't want to do this. Okay?
Thanks. Any other questions? So if no question,
maybe just a brief comment from my side. So it seems that your niobium-rhenium material looks as a quite highly performance, so good material indeed for detection. Yeah. But you work with different geometries in terms of the width of your microstrips.
Yes.
So that the recent studies reveal that also the type of edge.
Sure.
Might affect the nucleation of vortices and so on. So it would be interesting to take a closer look
at
the quality of your edges.
You're right,
maybe you could even improve if you suppress the nucleation of instability.
No, you're right, but you're perfectly right. Then this one, sure. These are the ongoing experiments. We are changing the width of the stripes, and then we would do a systematic study, of course. So this is done on iobirinium nitride in any case. But the idea is just as you said. I mean, we have also to see
And
this.
for which widths have you already evidenced the single photon nature of response?
1.3 nanometers.
Okay, so it's already a microstrip.
Yeah.
So very good.
Yeah, this is already. Okay, but we want to do as a function of the, as I said.
Okay, so thank you very much.
Okay.
Yeah.
Okay, thank you. Thank you.
So, therefore, this session is now closed. We have short coffee break, and I wish to thank all the presenters for interesting presentation and all attendants for active participation in the discussion. Thank you.
Okay, so we will continue after the coffee break, right?
I will co-supervise this, co-chair this session with Alexander Dubrovsky. The first talk will be given by Maksut Oklo from Cipse Technical University of Turkey, and with the title Multimode Strong Coupling of Superconducting Inverse Anapole Resonator with Magnetostatic Modes of Higgs Spheres. Please start.
Thank you for introduction. I also want to thank to the organizers for giving me the opportunity to present our work, some of our results here. And I will be talking about the strong, even in some conditions, reaching to the ultra-strong coupling regime of the coupling of magnetostatic modes of Higgs crystals with microwave photons. And here is my outline, and I will give a brief introduction about the light and matter coupling regimes, and also the hybrid quantum systems overview, and the HQS based on the magnetic materials, and then I will show some of our results, and I will finalize my talk with conclusions. Light and matter coupling is divided to 4 different regimes depending on the coupling strength of the systems, and each mode, if the decay rates of the resonance systems are larger than the coupling of these 2 systems, we are in weak coupling regime, and in this case the Purcell effects are dominant, and they have the applications at ultra-low threshold lasers, single photon sources. When the coupling strength between these 2 oscillating systems is larger than the decay rates, the dynamic of the system is dominated by the Rabi oscillations, and we are in the strong coupling regime, and maybe this regime will be very useful for the 2nd generation quantum technologies. And when we start to compare the coupling strength instead of the decay rates with the base resonant frequency of the systems, we are reaching to the ultra-strong coupling regime, at least 0.1 of the ratio. And when we increase the coupling higher than the base frequencies, we are reaching to deep strong coupling regime. Hybrid quantum systems can be on different platforms. For example, on the optical frequencies, they can be optical cavities with relatively low coherence time, or they can be Rydberg atoms with better coherence times, or they can be fiber optic cables. And at microwave frequency region, we have superconducting qubits, microwave resonators, and electronic spin ensembles. And at the radio frequency, they can be mechanical oscillators or the nuclear spins. The cavity magnonics is focusing on this region, and it's obvious that from this picture, for the quantum information processing or at the communication with the quantum computers, we need to transduct the information from microwave regime to the optical regime, because we are doing the processing at microwave frequencies and we are communicating at optical frequencies. And typically, the coupling between the microwave photons and the single spins is at the order of 1 Hertz. After the prediction of Soykal and Flat at 2010, with the microwave cavity and the nanomagnet, the coupling between the collective excitations of the spin ensembles, can be seen the coupling strength of these systems can be significantly enhanced by increasing the number of the spins which participate in the coupling, and also we can increase the coupling by decreasing the size of the cavity or by increasing the frequency of the oscillating systems. Sorry. And for reaching, after this paper, it got a lot of attention, and a couple of years later, Hong Tang's group from Yale and Nakamura's group from Tokyo published successive experimental results on microwave cavities with the Higgs sphere. And at strong coupling, the photonic resonator, the resonance frequency of the resonator does not affected by the applied magnetic field, but for the magnetic oscillations, it's linearly depends on the applied magnetic field. When the energy of ferromagnetic crystal is getting closer to the photonic mode, they couple to each other, and they gives the anti-crossing feature, and typically the anti-crossing feature, and they creates cavity magnon polaritons. There's a missing R here. And also there is this splitting is roughly defines the bandwidth of the Rabi oscillations. And another important parameter for the strong coupling is the cooperativity, which defines the ratio of coupling strength to the decay rates of the oscillating systems. And on this system, they reach to cooperativity for this system is around 3,000. Okay. And after a year of these experimental demonstrations, the Nakamura group also showed that the Higgs sphere can couple to a superconducting qubit in a microwave cavity, and these results are boosted the field, and in a decade, less than a decade indeed, there has been published too many different platforms for the photon-magnon coupling systems, and the explorations on the geometry, physics, and the platform lead to on-chip architecture, coherent information processing, and coherent transaction, respectively. And here we see the first studies, and also there are different studies, at least for the last years. The explorations are going on the on-chip architecture, for in terms of the coherent couplings. And also there has been some results which obtained for the dissipative couplings, and it provides us to non-reciprocity with the, indeed, this is the microwave diode, we can say it microwave diode, and on the coherent transductors, the magnons can also couple to the phonons, magnons, and for the optical photons with the whispering gallery modes. And these properties, indeed, it's very important, because if we want to transduct the information from microwave regime to the optical regime, we should couple the magnetic excitations, both the microwave photons and for the optical photons. And if you look to the magnons, or ferromagnetic excitations, the collective spin excitations of a ferromagnetic or a ferrimagnetic material, the equation of motion is defined by the Gilbert-Landau-Lifshitz Gilbert equation. We see here the Gilbert form of the dynamic of system. And first term drives the precession around the applied magnetic field, and the second term gives it to damping. And among maybe the most popular ferromagnetic or ferrimagnetic material is the yttrium iron garnet. It's known more than 60 years, and they are ferromagnetic insulators, and they have very narrow line width, in typically at the order of 1 megahertz. And they are transparent at the infrared, and they have high Curie temperature, and also they have large spin density. And if the excitations, microwave excitations on a sphere or a film, they can create the non-uniform excitations, which is called magnetostatic modes or spin wave excitations. And the energies or frequencies of, we see here the typical examples, some of typical examples of the magnetostatic modes of sphere, and their frequencies can be determined analytically by the Volcker method. Say. Sorry. And we designed the inverse anapole resonance structure by using the CST Studio Suite. And for fabrication, we used two different substrates. One is for the transmission line, and the second is for the inverse anapole resonator pattern. And we obtained the two deep, big deep here at these simulations at least. And these occurs by the inductively coupling of the inverse anapole resonator pattern with the microstrip line. And these two small peaks appears when we close the structure with conduction walls. Wow, 5 minutes. Okay. And this is our measurement setup. It allows us to apply the magnetic field at the parallel direction to the microstrip line, and the microwave analyzed by a vector network analyzer. And maybe I should. And at the preliminary measurements, we used an irregular shape of Yeek crystal. It was just a crack. And we obtained very large coupling with these systems, and with the as we see in the simulations, there is no magnetic field radiation at the center, at the first frequency, at the first resonant frequency, and we have a strong magnetic field excitation, microwave magnetic field excitation at close to the 14 gigahertz, and the loaded quality factors are seen here. For estimation the coupling strength, we use the dual mode. We used an input-output model for fitting the data, which is developed by the Professor Affronte group at Modena. And here we see the internal and external couplings, internal and coupling decay rates of the photonic resonant modes. and also the couplings to the resonant modes of each magnetic mode, and this equation can be expanded for the higher number of the magnetic modes. And at the first estimations, we used 3 magnetostatic modes. For the 8 GHz mode, we obtained around 500 megahertz of coupling, and the highest expected region, we obtained close to 1.4 gigahertz of coupling with the microwave photons and the YIG crystal. And we moved the sample to the outer conducting region, which is which the microwave magnetic field is effective at 7.5, more effective than the others. And we obtain here close to 900 megahertz of coupling, and these values are very close and also exceeds the strong coupling regime to the ultra-strong coupling. And I also want to show the other results with the YIG sphere. When we place the sphere at the center of the resonator, we obtain too many modes, and here we used 7 magnetostatic modes, and the couplings are changing from 600 to 800, and they are also very high coupling strengths. And with the same sphere, when we move it to the outer conducting region, we obtain the couplings close to 260. At highest one is 260, and for the other magnetostatic modes, we also obtained more than 100 megahertz of coupling. And the fittings indeed there are 3 different resonant modes here, and for this one is the strongest one, and when we focus in this part, the coupling strengths are relatively low, but they are still at the strong coupling regime. And this is indeed, I want to share with you for the possible contribution by you, because there are some unusual features. For example, one of them, and here what we have, let me show. We have a yttrium iron garnet bulk crystal. The dimensions are 0.3 and 1 millimeter, and the thickness is 100 micrometer. And we used a dielectric crystal at the outer conducting region for shifting down the resonant frequency, because there is another box mode here, and they overlap, and it's hard to be obtain the results. Okay, what's happening here? The coupling strength, okay, it's still high, close to 1.2 gigahertz. But the interesting thing is here, when we increase the magnetic field up to 100 millitesla, the upper polariton branch splits in 2 different branches. One appears at a constant frequency resonant, and the polariton branch is still there, but it's getting weaker. And also when we focus on this part, we see the too many magnetostatic mode excitations, and also at the high order magnetostatic mode excitations, we see here the unusual crossing features. And when we look to the evaluation of the ratio of coupling strengths to the base frequency on different systems, and we see in the last decade for these systems, we all obtained to reach to the ultra-strong coupling regimes, and our results are also a good promising approach to reach to the ultra-strong coupling regime. achievement of the ultra-strong coupling regime between sub-millimeter size crystal and the YVCO inverse monopole resonators with coupling strands reaching up to approaching to the 1.5 gigahertz, which is also the ratio of the coupling strength to the base frequency is more than 0.1. And the hybridization of multiple spin waves and resonator modes are also obtained. And in perspective, the pulse experiments and comparison with theory to unveil the effects of the ultra-strong coupling regime. And such architectures might offer a good testbed also for studying microwave to optical conversions. And here is the acknowledgements. I also would like to thank all of the co-authors, and thank you for attention.
Question?
Thanks for this nice talk. I have two questions. Why did you not use a YIG sphere, but use this randomly shaped piece of YIG? Because that generates a lot of random modes that make it difficult to analyze.
Exactly. It was about the purchasing of the YIG spheres indeed, when we fabricated the inverse monopole resonators, and the work is done at my postdoc research, and I take the scholarship from TÜBİTAK, and I had some limited time, and we start to look for YIG materials, and we find some cracks from some friends, let's say. And then the first measurements are started with
because I think it would just be clearer if you put it in a sphere. The other question is there anything in there where you would say it is actually quantum? Because, I mean, strong coupling can all be done classical. I mean, all this LRG type of dynamics. So what would you say we'd have to do to demonstrate that anything that you're doing has a quantum aspect?
Sorry, I couldn't get it.
So what do you think in your experiments needs to be done to demonstrate that there's actually a quantum effect? All the strong coupling regime can be explained classically, your LLG type of dynamics of the magnons and so on. So what is the idea in order to demonstrate that anything that you're doing has a quantum regime aspect?
Indeed, these are, as you said, are all in the classical regime. Also the temperatures are in the classical regime. And for the quantum, sure, I got my control complete now. Yeah.
Okay, thanks.
Thank you very much.
We'll thank the speaker again because of the time, and
thank you. Thank you very much.
So the next talk will be given by Kolsch Sebastian from Goethe University, Germany, and the title is Interfacing Effect in Magnetic and Superconducting Heterostructures.
Is it on? Okay, thank you. So very thanks for the kind introduction, and great thanks for the organizers of this conference, and to the session chairs for inviting me. The presenter, thank you. I would like to talk a little bit about a heterostructure consisting of quite common materials, but I think the combination of both is very interesting and promising. And for this, I would like to start with the introduction and motivation to both material systems and a little bit on the coupling between both. And I will then turn to the heterostructure based on a niobium and manganese silicon bilayer system, and talk a little bit about the preparation and the structural and transport properties of this system. And okay, so I think, why should one combine such interesting materials which deserve their own, like magnets or a superconductivity? I think the conventional types are quite pretty known, but if we combine both, we will emerge at new phenomena. We will see maybe some interesting things like magnon-fluxon coupling, which was just demonstrated by the group of Dobrowolski. And we have there the combination of spin waves, which are traveling in the permalloy layer, and on top of that, we have a superconducting niobium layer. And if we apply, or if there apply a little magnetic field, vortices will emerge. And what they have shown is indeed that due to the vortex lattice, which is just a periodic modulation of the magnetic induction, they see an opening of band gaps in the magnon dispersion. So they have really evidence that one can influence or can have a coupling between the fluxons, the vortices, and the magnons, which are traveling in a magnetic layer below. And one can go a step further, and one can just apply a small current and set the vortex lattice into motion due to the magnon force. And due to this movement of the periodic lattice, one can indeed have such interesting effects like a magnon-fluxon Doppler effect. So one can shift the magnon frequencies, which are then detected by this coplanar waveguides. Okay, if we just exchange the magnetic layer with not a ferromagnetic one, but a chiral magnet, and this was done on on this bilayer system. I think it was some iridium iron cobalt one, and one combined this with a classical superconductor, we see that in the chiral magnet under certain circumstances we can induce a skyrmion, indeed a Niel skyrmion, and this can couple to a vortex, or rather anti-vortex, because in the center of a skyrmion the field is in the opposite direction to the applied field, the applied external field. So we have a coupling between this anti-vortex and a chiral magnet. And indeed, it's a skyrmion. And what is very interesting that if one looks in the current voltage characteristics and one tries to obtain the critical vortex velocity from the Lakinov-Chinnikov instability, one can see that there is indeed a very great increase in this critical vortex velocity in the range of 1 or 2 kilometers per second. And another maybe very interesting point was proposed if one thinks on applications between the combination of magnetism and superconductivity. And a very easy application may be superconducting spin waves. So one tries to change the superconducting transition temperature just by the direction of a nearby ferromagnet. And normally, if you just live in the normal world, nothing is that easy. So you have a multiple layer construction between antiferromagnetic ones, buffer layers, and so on. So you end up with a stack of 10 or more different layers. And Pugach et al. Showed that under certain conditions, one can just have a bilayer system. And what the ingredients are just a chiral magnet, which they proposed is out of the B20 material family, in combination with some simple superconductor. And the idea behind this is that I have a helical ground state of the magnetization, and there are two possibilities for the wave vector, which is pointing towards the interface or parallel to it. And only the direction of the helix changes the superconducting transition temperature. And it was a hard time, but very recently, Julius Greve showed that it is indeed possible. They grew manganese silicon single crystals, polished them down to an atomically smooth level, and put a little bit niobium, about 20 to 50 nanometers on top. And they compared it to a non-magnetic or more easy magnetic material, cobalt silicon, and they have shown that it's indeed the direction of the helix which changes the superconducting transition temperature by about half a degree or more. Very interesting. So for those who are not familiar with the B20 materials, and manganese silicon is the most prominent member of it, just imagine a very easy FCC lattice, and we are looking along the 111 crystal direction. And if we now alternately compress and stretch it, we end up in a unit cell which is like this one, which is essentially the manganese silicon B20 type. The interesting thing about this crystal family is that there's no inversion symmetry anymore. And due to the lacking of the inversion symmetry, one can obtain a Jaluzinski-Moria interaction, which just favors a perpendicular alignment of the spins, which is to be combined with the classical parallel alignment, the direct exchange interaction. And one obtains the very interesting magnetic phase diagram with a small skyrmion pocket, we all know, I think. But if we now go to manganese silicon thin films, which are epitaxially grown, the story is a little bit different. And there's a lot to say about it, but I think we just concern the case for magnetic field is pointing in the out-of-plane direction, and we lose the skyrmion phase. And it's, I think that one can say it's safe, but it's still under discussion. So if we end up with the phase diagram, there is some small helical magnetic phase. We apply then a magnetic field, and the spins align a little bit along this field direction. We end up in a conical state, and if we just raise the magnetic field, we end up in a field-induced ferromagnetic state. Okay, so if we now turn to the preparation of our heterostructure, manganese silicon thin films are quite difficult to prepare. We use a classical MBE approach, molecular beam epitaxy. Our growth chamber is pretty clean. We have base pressure of around 1 E minus 10 millibars. We start with a pure silicon 111 substrate. We anneal it at around 900 degrees Celsius to clean off any contaminants and especially the native silicon oxide top layer. And if we just let it cool down to the further deposition temperature of 200 degrees C, and we're doing read, one can obtain this very nice 7x7 surface reconstruction. And this surface reconstruction is really crucial to obtain clean epitaxial manganese silicon thin films. And it points out that we have indeed a very smooth and virtually contaminant-free surface. We start then the co-deposition of both sources, manganese and silicon, and here it is quite essential to match the fluxes very well. A little bit off and you end up with another binary composition. We slowly grow the thin films with about 1 nanometer per minute, and when we perform read on these manganese silicon thin films, we can indeed see that if we rotate the sample, we have a threefold surface symmetry as expected for the 111 direction. The main crystal axes are rotated against the silicon ones by about 30 degrees, and one can obtain even the second order lower circle, which points out that the thin film is very well ordered. Okay, so if we just look on the high angle X-ray diffraction, we can see in the out of plane that we have only the 111 and the second order reflex, so it's indeed a pure and epitaxial thin film. If we perform additionally in-plane asymmetric scans, we obtain the epitaxial relationship we already have seen in the read, and we have no contaminants and especially no crystalline component from the silicon capping layer we have just put on top. Okay, if we look on the surface and we want to see how thick it is, we employ X-ray reflectometry, and we can obtain the Kiesig fringes of at least up to 6 degrees, which is quite high. And if you fit it, we see that's a 23 nanometer manganese silicon thin film, which is very smooth. If we just look on the lower oscillations between the 111 reflex, we get a coherent thickness, about 22 nanometers, which means that the total thin film is nearly single crystalline in the out-of-plane direction, which is very nice. Okay, if we now want to put niobium on top, we just transfer our sample without exiting the vacuum system into our sputter chamber, which has a base pressure a little bit higher, about 1 E minus 7 millibars. We choose a working pressure around 5 E minus 3 millibars and a deposition temperature of 300 degrees C. And as already known in the sputtering process, we are much growing faster, about 5 angstrom per second. If we now just return to the MBE chamber, we see via read that there seems to be some diffuse lines, but some spots as well. If we rotate the sample, we see that there's no single in-plane orientation relationship to the manganese silicon thin film, but there seems to be a kind of textured growth. And afterwards, we just cap it again by silicon. So for the second type of bilayer, we end up with, again, manganese silicon in the 111 direction, and one can obtain the niobium 110 reflexes. Okay, so as we have seen, we have an out-of-plane orientation chip, which is quite typical. We have a BCC metal niobium, which grows 110 oriented on a quasi-FCC 111 surface, the manganese silicon. And typically one would just characterize it by a certain orientation relationship, which may be one of these. But since we have not seen it, there seems to be many possibilities for this in-plane rotation. And if we take a deeper look into it, we see again some Kiesig fringes now only up to 3 degrees, but we can say that we have a thin film about 33 nanometers manganese silicon with 50 nanometers of niobium on top. And if we just look at the surface via AFM, we can see an RMS roughness below 2 nanometers. So it's quite smooth and a very nice heterostructure. If we just compare it with the rocking curve and the full width at half maximum of the 110 reflex of niobium, which is very high, about 8 degrees, we see a certain kind of mosaicity and tilt of all the single crystals. Okay, if we now turn on the transport properties, we just use UV photolithography and some low energy argon ion etching to prepare our 6-contact hall bar structure with a cross area about 30 by 100 micrometers. And now we compare the pure manganese silicon thin film, 23 nanometer 6, which is blue curve, and we see we have a residual resistivity about 25 microohm centimeters, which is very low, and indeed a residual resistivity ratio about 8, which is very high for this kind of thin films. And as can be seen here from the kink in the curve, we obtain the helical phase in the thin film at about 44 Kelvin, quite as expected. If we now turn niobium on top, where we end up at a resistivity about 10 microohm centimeters for niobium, still a quite good residual resistivity ratio, about 3.5, and a superconducting transition temperature, which is indeed quite high, about 7.6 Kelvin, and quite narrow, about 0.1 Kelvin wide. So the thin film seems to be quite robust. Okay, if we now apply a magnetic field in the out-of-plane direction, we see indeed, as expected, the shift of TC, and if we now fit it, we end up with an upper critical field at 0 temperature at about 1.4 Tesla, which leads to a coherence length at about 17 nanometers. If we now perform many current voltage characteristics and we track the flux flow instability, we obtain for the bilayer system a critical vortex velocity above 2 kilometers per second, which is quite high. And indeed, if we compare it for the simple single layer of niobium, same thickness, nearly the same parameters, same TC, and so on, we obtain only about 0.5 to 1 kilometers per second. So what we obtain due to this non-trivial magnetic state is a quite high increase in the critical vortex velocity in the niobium layer. Okay, so I hope so far I could convince you that we have prepared high-quality manganese silicon thin films on the substrates. We have the epitextural relationship shown here. And for the first time, it was possible just to grow a textured niobium 110 oriented thin film on top, which shows quite promising superconducting properties. We are not in the dirty limit. We are not in the clean limit. We are something in between. So the raise of the critical vortex velocity is not attributed to this dirty limit, but it's rather attributed due to the non-trivial magnetic state. And so what we are planning to do in the very near future is we want to perform a more detailed investigation, especially how we can just influence or manipulate the vortex dynamics, and especially with the focus of a thickness dependence of the magnetic layer and the superconducting layer. And one can ask the question, what is the reciprocal influence? And as already mentioned, in manganese silicon thin films, there seems to be no skyrmion phase in the out-of-plane direction. But if we now have a periodic modulation due to the vortex lattice, one can assume or maybe speculate that there may be a reciprocal influence on the magnetic properties of manganese silicon as well. So we plan some magnetization measurements and many, many more. So with this, I want to thank all my collaborators and you for your attention.
Thank you. If there is any questions?
Very nice. Do you have some indication about the magnetic inhomogeneities or the magnetic configuration that can really play a role in this increase of the critical velocity?
Sorry, I'm not sure if I understand it correct, but the to rule out the possibility of the disorder influence. Okay, so we just tried a very small comparison between niobium on manganese silicon on silicon and niobium directly on silicon. And in both cases, the TC is essentially the same. We have nearly the same upper critical fields and so on. So the property seems to be quite essential. And if we look on the X-ray diffraction and so on, we see surely a global image of the thin film and so on. But they seem to be very, very comparable. And so the only change between both is the magnetic layer and the influence of it. So this raise in critical vortex velocity seems to be purely attributed to the different magnetic states we have. I hope this was.
Okay, sure. Yeah, that's what we have with permalloy. I mean, just this
absolutely.
Yeah.
And
okay.
Yeah, but I think there was a little bit more of disorder and so on. And yes, so we tried to rule it out, and that's why we did this experiments of only niobium on silicon, just to have a direct comparison. But thank you for your question.
Yeah, yes. I think you have a lot of room to go into thinner, thinner niobium layers. That
Absolutely.
Will give, yeah.
You see it.
Yeah.
It's all planned, but time is running, you know.
Okay, thank you.
Okay, we take a second question, Alexander.
So my question is probably in connection and very closely related. In the motivation slide, you showed this superconducting spin valve effect. So maybe just having angle resolved measurements would allow to answer the question whether there is some effect on the critical temperature and whether you can modify the magnetically intrinsic and homogeneous, so you know your uniform state to see the different effects, and then to exclude whether it is just a magnetic layer or it is the presence of some particular periodic pattern on the critical velocity. So it's interesting to look at, so just a comment on that. So
thank you. Yes. Indeed, it's quite a playground to just distinguish new phenomena or maybe just a combination. We'll see.
Okay, let's thank the speaker again. So the next talk will combine both contributed talk. It will be presented by Arkady Zhukov from the University of Basque Country, Iker Basque, Spain. And the title is Fabrication and Post-Processing of Heusler alloys, magnetic microwires, and ultra-fast domain wall dynamics in magnetic microwires.
Thank you very much for your introduction. So you can see the authors of this talk. So we are from Spain, also picture of San Sebastian. And it's my pleasure to participate in this conference on quantum technologies and materials. You can see the introduction, which consists of outline of my talk, which consists of introduction, fabrication techniques, and in fact, both talks are somehow related. Therefore, probably I will skip this kind of details in the second talk, and also a picture of San Sebastian. So in our laboratory, we worked a long time ago with so-called glass-coated microwires. This material is composite materials consisting of metallic part, metallic nucleus coated by glass. And this is because of peculiarity of the technology. In this technology, we first prepare the desired alloy, then melt it by inductor, and then draw glass capillary with metallic nucleus inside. In this case, we can get quite thin and continuous microwires coated by glass. You can see here some picture, the most modern machine which we have in our spin-off company. And the features of this technology that from 1 gram of materials we can produce about 1 kilometer of continuous metallic microwires. And of course, the technology is quite fast and inexpensive, so we can produce about 100 meters per minute. And in the case of amorphous materials, we can have very soft magnetic behavior, also fast dimensional propagation, which I will speak in the next talk. And also recently we tried to produce this technology, Hussler alloys, microwires, because of interest of production of thin materials from Hussler alloys. So I already mentioned that most attention had been paid up to now to amorphous, so-called nanocrystalline materials, and recently Hussler alloys attracted attention, and this is because this technology allows to produce quite different geometry from 100, in fact 100 nanometers to 100 micrometers, diameter of metallic nucleus, and quite a wide range of chemical compositions. And so we are looking for new properties in this kind of materials we've produced from Hussler alloys. So as regarding the amorphous materials, which quite extensively studied recent years, the most attention has been paid to so-called giant magnetic impedance effects. So you can see the application of even very small magnetic field can produce a huge change of impedance of such materials when we measure at high enough frequency, about 400–500%. However, iron-rich materials present this squared hysteresis loop and also very fast dimensional propagations, which I'll speak in the second talk. Actually, there are already a few industrial applications of that materials. For example, this is JMI chip, which produced by EC Steels. You can see the size. In this case, the microwire is placed here, and it's excited by current, and then this pickup coil receives the signal, which is of diagonal component of magnetic impedance effect. And they already use in cell phones for games or in smartwatch. You can see here some pictures of EC Steel Corporation. So if you compare the cross-section of these materials with conventional materials, you can see that they are somehow a little bit thicker than thin films, however much thinner than conventional rapidly quenched materials, which could be produced in amorphous state, for example. And this means that there is certain interest of the extension of this technology to obtain new kind of materials using this technique. So in fact, interest in Hussler alloys is coming exactly from what I already discussed, the possibility to observe magnetic field-induced strain, magnetocaloric effect, and also recently, for example, last 2 years we studied so-called cobalt-2 based microwaves, which can present quite high accurate temperature, above 100 Kelvin, and also higher magnetic moment. So you can see some publications on this topic also in this slide. And in fact, one of the main advantages of this technology is that there is a lot of efforts to produce Heusler alloys with low-dimensional materials, thin films or wires. And you can see one of the attempts which discussed in advanced materials paper. The problem is that, for example, nickel manganese gallium alloy is quite brittle, and therefore conventional method to reduce the dimensionality are useless for production of that materials. And this is one of the motivation of our job. And another motivation is that there are different factors which can affect the refrigeration machine performance. For example, one of them is to enhance the magnetocaloric effect. However, the other one is just to enhance the interface to heat exchange because of thin dimensions of materials. And so first to volume ratio, and then microwires or thin films could be very good candidates for these applications. Well, probably it's almost the same. So in this presentation, in this paper, we used different techniques to characterize magnetic properties and to extract magnetocaloric effect through magnetization curves of the materials. We use also X-ray diffraction to see the structure, and also EDX to see the composition. In this picture, we present nickel manganese gallium microwaves which produced these techniques. In this case, the diameter was about 22 micrometers, and you can see the cross-section of this material. And here are some results. So first of all, we characterized the as-prepared materials. And in this particular composition, we found small histories which we didn't know what is the origin of this. However, for example, magnetization curves didn't show saturation even at very high magnetic field. It means that these materials are probably not homogeneous. To evaluate what happened with the materials, we also measured the resistivity, electrical resistivity. And in the range where we have these small histories, we observe this typical hysteretic anomaly, which is signature of martensitic transformation on that kind of materials. And we try to also to somehow to process these materials to enhance the magnetic properties. And what we observed that after even any annealing, the hysteresis will become typical like ferromagnetic even at nearly room temperature. It means that the magnetic character of these materials is significantly affected by annealing of these materials. However, almost no hysteretic anomaly was observed. Instead, there is some kind of peak just before the Curie temperature, and this change of magnetization was just quite abrupt. So we try to modify the annealing temperature of these materials, and finally, at certain conditions, at more elevated temperature, we observed finally this hysteresis, which is typical for martensitic transformation, and also this change of hysteresis loop when we change the frequency, and again the Curie temperature was very close to room temperature, which could be attributed to this martensitic transformation on these kind of materials. Here are similar features of materials which have been annealing at similar conditions, but a little bit higher temperatures. And these materials also present giant magnetic resistance features, like shown in this picture. And it disappears above the Curie temperature of materials, and it could be as high as about 3%. Not very high, but still could be attributed to this very thin ferromagnetic grains in, for example, non-magnetic matrix. And the magnetocaloric effect, we try to evaluate from the magnetization curve, so using the typical protocol. And the magnetocaloric effect was not very big, but still we got some acceptable values of magnetocaloric effect. And from the point of view of structural characterization, we observed that the structure of these materials have been changed. So first, of all, we have quite broad peak, which could be coexistence of amorphous phase and the almost unknown DCC phase. And then upon annealing, we observe this change of the X-ray diffraction. This is the main peak. And finally, we got some amount of right of FCC phase, which could be responsible for martensitic transformation, which we observed by magnetization measurements. Also, we were able to measure directly change of the temperature using another technique, and we observed that indeed these materials present magnetocaloric effect in vicinity of Curie temperature. One of the interesting features of these materials that they present dependence of Curie temperature on annealing conditions. Here you can see the samples annealed at different conditions, and you can see the Curie temperature is a function of the annealing temperature. Therefore, for example, one of the attempts to enhance the Curie temperature, to enhance the range with which we have phase transitions could be to mix the materials prepared by this method. In this case, we can have extended range of magnetic transformation, because different materials with nearly a different temperature can present different Curie temperatures. Well, these features, for example, a huge effect of annealing could be attributed to strong internal stresses which involved in this fabrication technique. So once we quench together metal and glass, both of them metallic part and glass shrinks together. However, the glass has much smaller temperature expansion, thermal expansion coefficient than metallic core. Then there are some strong internal stresses, mostly of axial origin within the metallic part of this composite microwires. And also, if we increase the thickness of glass with this fixed diameter, we increase these stresses mostly of axial origin. This is the distribution of stresses along the radius of the microwire. And this could be the reason of such difference of these magnetic properties and magnetocaloric properties of these thin microwires as regarding the bulk materials. So we did several attempts to prepare different Heusler type alloys with indium, nickel, manganese, indium, for example. You can see again these materials present huge effect of annealing on magnetic properties as shown here. And finally, I will present last results on cobalt iron silicon microwires, which we also prepared using the same method. This time we were much thinner, about 4 micrometers. And again, we observed coexistence of amorphous and crystalline structures as prepared materials. And then upon annealing, we observed evolution of the structure and increase of the content of a crystalline phase. So we even tried to estimate using the area of the peak to the content of crystalline phase. It was about 64% as prepared materials. And what was interesting for these kind of materials that they indeed present quite high Curie temperature, even we were not able to measure. So this was the limit of our PPMS system. So we just tried to have approximation. It was about 1050 Kelvin for these kind of materials. And these materials also present some effect of annealing. For example, we can observe how it changed the hysteresis loop from almost rectangular for us prepared states. There is kind of irregular hysteresis loop and intermediate annealing temperature, and then it's become again similar to us prepared states. It means that probably there is kind of the development of recrystallization of these materials, which could be responsible for this transformation. And here we can see the modification of X-ray picture of these materials. We observed that the grain size is increasing upon annealing, and we used for this estimation the Bayer-Scherer formula for these materials. Recently, we also tried to prepare this kind of nickel manganese 2 phosphorus silicon boron microwires. And here are just recent results showing that still we're able to produce this kind of materials. So resuming, coming to conclusions. So this technique has several advantages. For example, possibility to prepare long and thin microwires. In this case, the length could be up to 100 meters for the case of Western alloys. And these materials can present enhanced surface volume ratio, considerable magnetic resistance and magnetocaloric effect. However, there's some disadvantages that there are strong stresses which need some special attention. These stresses should be somehow released to optimize the structure to obtain magnetic transition in these kind of materials. And also, we have a problem with manganese evaporation because the process duration is few minutes. So during this process, we have change of stoichiometry of the materials, and this should be somehow improved in the future. And here are just the conclusions. So this kind of microwires present some interesting features like magnetic resistance, magnetocaloric effect, and the Curie temperature could be modified by post-processing of these materials. And probably the main interest is possibility to produce thin and long materials in which the glass is flexible at that thickness and could even improve the mechanical properties. So this is the first talk. I don't know if I will continue.
Maybe we have some question.
Yeah, please.
Any question on this part? If not, we may continue with the.
Okay.
Yeah.
No, I can take later, so I will continue. So I'm sorry, that, the second talk should be given by Valentina, but she asked me to give the same talk. So the second talk is more related with the amorphous materials. So the fabrication technique is the same, however, the authors are different, and also the topic is somehow different. So here you can see again the picture of San Sebastian. I forgot to say that we are in this area of Spain, very near to France, in the north, in the Biscay Gulf, in the north of Spain. You can see the outline of this talk. And in fact, magnetic wires are known since many years, and most of the interest have been related with the domain wall propagation, which we have been reported by even Sik-Tuk Tongs in one of the first paper on domain wall propagation in magnetic wires, and also on giant magnetic impedance effect, which somehow have been described many years ago, but then forgotten and recently somehow rediscovered, and then now even used for industrial application. This, in fact, I can skip this transparency. The important thing that in the case of if the phase diagram have deep eutectic and the melting temperature is low enough, when we apply rapid quenching from the melt, we can get amorphous, we can fix glassy states at almost at room temperature, and in this case we can get the amorphous structure. And this is quite relevant for magnetic properties. For example, one of the families of such microwires with positive magnetic restriction presents so-called magnetic bistability effect. It means the hysteresis loop is perfectly rectangular, and even if the amplitude of magnetic field is below the switching field, we don't have hysteresis loop. And this have been explained. Here is the live hysteresis loop of real iron-rich microwires with positive magnetic restriction. And this had been explained because of the peculiar domain structure, consists of single axially magnetized domain. However, if we have real sample with finite length, we have such kind of closure domains which also affect the magnetization reversal of these materials, as I will show later. Then in these materials, once we apply magnetic field and move from positive to negative, there is a kind of deepening of domain wall and then fast domain wall propagation along the sample. And the motivation of this part is related with possibility of use of controllable and fast domain-level propagation for different logic and memory applications shown here, so well-known jobs of different teams. And even if we compare our microwires with circumferential cross-section with so-called nanowires made from permalloy, but however, this kind of nanowires are in fact not wires exactly, but they have, because they have rectangular cross-section with thickness and width of similar sizes. In our case, we have much faster domain-level dynamics, and in this case, about 1 order faster domain-level propagation in the dependence on domain-level velocity on magnetic field. And even this propagation is observed in smaller magnetic fields. So we studied and therefore domain-level propagation in amorphous iron, nickel, and iron cobalt rich microwires. And we employed 6-like experiment in which we place several coils along the microwires, and then we can follow the diamond wall which propagates along the sample. And even the peak which correspond to traveling of the diamond wall through such pickup coil could be useful for analyze the shape of the diamond wall in these kind of materials. So in fact, we modified this technique. We placed several coils along the microwires to see how it propagates. And this is because, in fact, diamond wall could be nucleated even in any part of materials. However, for this we have to apply local strong enough magnetic field. And so we can inject the diamond wall in this case in different part of materials, and then to see what happened with the propagation of that diamond wall. And if we now measure the nucleation profile, so this is the length of the sample which we used, about 100 of micrometers, we can see that the nucleation field is smaller close to the ends of the samples. And there are also some kind of fluctuations of this injection or nucleation demand field of nucleation of such domains inside of microwires. And this is because probably of the defect. For example, we were able to move the microwires along the short nucleation coil to see that these picture fluctuations are typical for each sample. It means that it reflects the real defects in each samples. And then we tried also to analyze what kind of defects they are. And even, for example, we were able to have a relationship between domain wall propagation between this case first to second and second to third domain wall pickup coil, and then to find the place where is the domain wall nucleation takes place. So its picture is similar to Walker limit. However, this is because the additional domain wall nucleates in the head of propagating domain, in this case between first and second coil, and you can see good relationship between this field of minimum nucleation field and this change in the domain wall dynamics in this case. So it means that the effects are quite relevant for this domain wall dynamic in this kind of materials. So we used different compositions, and the reason that we needed to have positive magnetostriction. However, the magnetostriction of these materials depend on the composition. So playing with the ratio between iron and nickel and iron and cobalt, we can change the magnetostriction of the materials and also change the hysteresis loop. However, all the hysteresis loop presented this squared hysteresis squared shape in all of these materials, and this is because of different magnetostriction constant of the materials. So in our case, I already mentioned in the previous previous talk, there are two important parameters: magnetostriction and also internal stresses. Internal stresses, I already mentioned before, depends not only on the composition of glass and metal, but also on the ratio between thickness of diameter of metallic nucleus to total diameter. In this case, increasing the glass coating thickness, we can enhance the internal stresses of the materials. And this gives us additional possibility to tune the properties. So we wanted to evaluate to see how is the effect of magnetoelastic energy on the manual propagation of these materials. For this purpose, we first tried to apply stresses during the manual propagation. So this curve, the black one, is the dependence of the manual velocity on magnetic field without any stresses. And now if we apply a magnetic field, stronger and stronger, you can see this decrease of the manual velocity and the slope. The slope, in fact, is the manual mobility in this case. And you can see also the pickup signal from pickup coils, how it changed when we apply the stresses. The next step, we try to use the same microwires with the same row ratio. It means that the same internal stresses, however, the different magnetostriction coefficient, different magnetostriction. So in this case, the magnetostriction was almost twice different. And you can see that the slope was again different. So it was high in the case of smaller magnetostriction. And even the slope was almost twice different. So it means that there is somehow correlation between the magnetostriction volume and the manual mobility in this case. The last one, we tried to fix the magnetostriction. However, we're playing with internal stresses. And again, the highest row ratio, the smallest internal stresses correspond to the highest manual mobility. In this case, it means that the manual mobility is affected by magnetoelastic energy. So internal stresses and magnetostriction of the material. So we checked it again in a iron-rich composition with two different magnetostriction, and again the slope was somehow different in these two kind of materials. And also there is some quantitative agreement with this approximation. Finally, we choose the materials with the quite small magnetostriction to get the highest values of the manual dynamics of the velocity, and in this case we observed the manual velocity up to 2.5 km per second. So it means that magnetoelastic energy is quite relevant for the manual dynamics of these materials. And this could be easily understood if we consider the damping relationship with the magnetic anisotropy. In the case of amorphous materials, anisotropy is mostly related with the magnetoelastic energy. Okay. So, another way to enhance the manual dynamics was just stress relaxation. In this case, we anneal the materials, and you can see again drastic increase of the manual velocity and mobility, and the origin should be the same. By the way, our materials still keep amorphous structure. There's a X-ray picture showing that our materials, the structure was almost the same as in as prepared state. So one of the ways to enhance the manual dynamics is stress annealing. In this case, one can introduce transversal magnetic anisotropy. And you can see again the picture showing that even higher values of the manual mobility could be observed in this case. And you can see the dependence of the manual mobility on time of annealing. So quite large values of the manual mobility have been observed in this case. And this is because transverse magnetic anisotropy, which affect the manual dynamics in similar way as the transversal magnetic field. So, by the way, this technique allows to modify the history slope from almost rectangular to almost inclined, shown here, meaning that the stress-induced anisotropy could be very strong in this case. There are different approaches to origin of this stress-induced anisotropy. The most common one is related with pair ordering. In amorphous materials, there is kind of short ordering change upon the annealing on the stress or on the magnetic field. So what could be another interesting feature of these materials? For example, we can change the temperature in the furnace and then anneal our microwires a few centimeters long, and they have different history slope in different part of these microwires. And then, for example, what we did, we annealing these kind of materials Okay, this is as prepared materials, and you can see the sequence of the peaks, which correspond to the normal domain wall propagation. Domain wall velocity between first and second and third pickup coils are the same. And here you can see the profile of magnetization. Now we apply the stress during the annealing and anneal only a short part of materials. In this case, we can introduce the defect which is shown here. So it's the decrease of the nucleation field in some area of the materials in which we under stress apply local annealing. And in this case, the sequence of the peak is in the same sample is completely different because we can now nucleate the domain wall in the place where we can create this artificial defect and then inject the domain wall by magnetic field. And in this case, the domain wall propagation will be completely different. Okay, and another interesting feature of this stress annealing is that the gate in which the domain wall propagates could be decreased because this transverse anisotropy, and therefore even the shape of the domain wall could be affected by the stress annealing, so it's becoming shorter and it could be also useful for the applications. Well, I will go a little bit faster because I still have a few slides. The origin of so high domain wall velocity should be understood from the following. So, in fact, the domain wall is not abrupt, and there are few models showing that the shape of the domain wall is quite elongated. In this case, the normal velocity is much smaller than the real values of domain wall velocity, and this could be the reason of such elevated values of the domain wall velocity. And analysis, precise analysis of signal from pickup coils could be important. So in this case, we observed that the values of length of domain walls from 10 to 60 diameter of microwires, and it's affected also by applied magnetic field. Okay, just a couple of slides. So what I told before was related to iron-rich samples with spontaneous magnetic bistability. However, in the case of cobalt-rich materials, the magnetic bistability could be induced by annealing. And these kind of materials are relevant because they have different domain structure. So axial core is surrounded by also domain, outer domain, but in this case the orientation domain is circumferential. And this gives us possibility to realize in these materials so-called current-induced domain wall propagation. But in this case, the domain wall propagation is related with a worsted field, which is allows to change in magnetization in the outer domain shell, and then you can observe also propagation in the inner domain. And in this case, here are two pictures, so you can see the difference in the pickup coils. In this case, we just apply the current without magnetic field. And in this case, the values of the domain wall velocity were up to 2.5 kilometers per second, as shown here. And these materials with induced magnetic bistability could be quite interesting, not only because of elevated values of the domain wall velocity, but also that if you now apply the stresses, the domain wall velocity increase on the application of stresses in this kind of material. So I'm going to conclude. So we studied the properties and domain wall dynamics in different families of magnetic microwires. So the high domain wall velocity up to, in fact, to 4 kilometers per second could be observed. And there are different ways to tune this domain wall dynamic in this kind of materials by annealing, stress annealing, induced anisotropy, etc. So thank you for your attention.
Thank you. Is there are any questions?
Thank you for your interesting results. I'm wondering, so you succeeded to suppress this Walker breakdown and to accelerate domain walls to kilometers per second velocities, but you can also manipulate or keep the front of the propagating domain wall close to a straight line, or it still will be this, as you showed, special shape. Can you somehow tune the shape of the propagating?
Exactly. One of the results, one of the slides, with transverse anisotropy, we can make it shorter, but it's still elongated.
But which parameter is a control parameter so that you can engineer, so to say, the front?
Magnetic anisotropy. So, but in this case, we have transverse magnetic anisotropy, and this transverse magnetic anisotropy affect the shape. So it's as strong anisotropy we have as abrupt the domain wall. But still it's elongated, so it's few diameter of
So
micro.
also in relation to geometry of a particular...
related to geometry, and also in the case of stress-induced anisotropy, the gates in which the domain wall propagates becoming smaller. And it's also related, so it's in fact affected by the diameter of the inner core. Not the geometry itself, but and so we can play with different factors.
Okay, thank you.
Any other question? Jacob?
Thank you very much. I wonder how thin can you make these wires, and how would this change the anisotropy or the geometry of the domain walls?
Okay, as thinner microwires, as shorter the domain wall. And in fact, we usually working with about 10 micrometers, but there are some jobs which could be reduced up to 100 nanometers, the same technology. So, but of course, we will have much shorter materials, but still, for example, one of the results we presented was about 2 micrometers, so 2,000 nanometers.
And what would happen to the transverse anisotropy if you go to the nanometer range?
Yeah. There are different factors. For example, one is the interface between glass and metal. So it could affect. So in fact, this interface thickness is about half a micrometer. So in the case of quite thin dimensions, the interface could be relevant. I mean, the area between glass and metal. And another one, of course, the stresses. As smaller the diameter, as stronger the stresses. And so it should be studied. But also the shape anisotropy is quite relevant in this case. So there are different factors. I cannot say exactly what happened with the shape, but...
Okay. Thank you very much. Yeah. Thank you.
Yeah? So maybe I have a question. So how is the stress is applied? So in the microwire with the encapsulation? So you... Well, when we measure during the measurements, we just attach some weight to the microwires, and there are tensile stresses, only tensile. In the case if you deal with internal stresses, the most of them in the most of the metallic diameter is also tensile, because both glass and metal shrinks together. However, glass shrinks much smaller than metal. Yeah, during the fabrication, but we can somehow release these internal stresses and also play the thickness of glass. But this material is essentially a composite material. Yeah, another question just from ignorance point of view. Can this encapsulation of glass be used for example, to drive optical photons? Or yeah, we now trying to... So we can... Oh. So yeah, yes, in fact, the glass is used for us to make these materials still amorphous, but thin as possible. So use rapidly quenching, but we are now thinking how to use the glass, in fact, for different applications as well. Yeah. For example, we have now a project when we try and also to mix these microwaves with carbon fibers, etc. Okay, thank you. Interesting. Let's thank the speaker again. And with this, we close the session. Thank you all for your attention and to be up to till now. So thanks.